It's Magfest weekend again, which means that I haven't had a lot of time to work on GameMaker stuff this week. So I think I'll copy what I did last year and release another compilation of 3D collisions in GameMaker. This one mostly pertains to triangles, triangle meshes, and spatial partitions which allow you to speed up triangles, triangle meshes, and collision worlds as a whole. I'll put chapter markers in the description so that you can quickly jump to a section that you're interested in, and I will see you when I get back. Also, in listening to these playing back, I find it fascinating how my voice seems to change from video to video despite my recording setup having stayed pretty much the same over the years. Feel the rhythm, feel the rhyme, get on up, it's game dev time. I cannot believe I decided it was a good idea to open with that. Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games. Let's talk about 3D collisions in GameMaker. So this is going to be the beginning of what I believe I called Act 2 the last time of this 3D collisions in GameMaker series. The first act, if you have not seen it already, was all about figuring out collisions between basic points, figuring out if basic shapes were intersecting in GameMaker, including the point, the sphere, the axis allowing bounding box, which in common parlance you might just call a brick, and the plane, as well as a ray cast and line segment cast into each of these shapes. And Act 2 is going to be all about bringing triangles into the mix. We are going to be working out intersections between triangles and shapes, triangles and rays and line segments, and of course triangles and other triangles, as well as 3D models built out of lists of triangles, and ways that you might want to organize triangle data in order to speed it up. Then at the end of the series, and I haven't decided exactly what I want this to look like yet, but I do want to do another one of those collision world videos, so that we can see how this might work in an actual game. Okay. So if we look back at this test program, I have gone ahead and added a couple more test shapes for triangles, and they don't really do anything yet. They don't detect collision yet. I haven't even written any code to allow you to move these around on the screen with the arrow keys so that you can test them in different locations the way I have with the other shapes. We'll get to all that in due time. First, let me just quickly show you what this looks like. We have the test triangle. A triangle is composed of 3 points, 3 vector 3s, 3 points in space, and then instead of the test class using a default shape loaded from the file, we are just going to be building a triangle vertex buffer out of those 3 points. They're lying flat on the ground. The normals for the triangle for lighting purposes are just pointing straight up in the air, 0, 0, 1. I will get to generating triangle normals soon enough. That is something that may turn out to be fairly important fairly soon. And then, of course, down here, when you come to draw the triangle, you just vertex submit it, set the matrix to the identity matrix. Backface calling is of course, turned off because I don't want these triangles to be double-sided, but that's not going to be the focus of today's video. If you have not yet watched Act 1 of this 3D collision series, I highly recommend going and doing that. I'm going to be operating under the assumption that everybody who watches these videos from here on out has and is familiar with things such as the vector class and some of the other practices that I've been following. Naming conventions and whatnot. I'll have links to the beginning of the playlist in the video description and in a card and that sort of thing. Otherwise, assuming that everybody has gone and done that, let me open up the call_shapes code file. We are just under 300 lines of code in this file. This is going to be quite a bit longer by the end of Act 2. Let's start out by defining a triangle. So I'm going to say function call triangle. This is going to be a constructor function for triangles. Triangles, as you all hopefully know, are composed of 3 vertices, 3 points in space. I'm going to name those A, B, and C in the constructor. Of course, the constructor has to be actually marked as a constructor. And then we are going to be, the first thing that we're going to do is self.a is going to be A, self.b is going to be B, self.c is going to be C. We're going to take these constructor parameters and save them to instance variables of this triangle struct. That's all the information that defines a triangle with an asterisk on it. I'll get to the surface normal later. But next, I'm going to define a couple functions. One is going to be static checkpoint, and that's going to be equal to function which takes a point as a parameter. I'll fill in the body of that function momentarily. Next, we're going to do something that should look very familiar to those of you who have watched the first 8 or so videos in the series. Check sphere. It's going to be a function that takes a sphere as a parameter. Check add for the axis aligned bounding box, and check plane for the plane, checking collision between a triangle and a plane. Next, there is going to also be static triangle. That's going to be a function which takes a triangle as a parameter. We're going to also have check ray and check line. Ray casting functions, these are going to take a slightly different form in addition to just the ray instance of a struct that we're going to take as an input parameter. There's also the hit info, as with ray casts against the other shapes. Again, we will fill that in when the time comes, and check line is going to check for an intersection between a triangle and a line segment. And then, of course, we need equivalent functions in some of the other basic shapes. So this is in call point. We're going to define static triangle is going to be a function which takes a triangle as an input parameter. We will fill that in when the time comes, as I said, and all of the other basic shapes are also going to take. And I'll put this function beneath check plane and above check ray and all of these classes. The sphere is also going to have a check triangle function. Really should call them methods. The axis align bounding box is going to have a check triangle method. The plane is going to have a check triangle method, and that brings us back to where we started. And also the other rays. So I will give the ray a check triangle method. This is going to also take a hit info struct as a parameter, but we'll worry about that later. And check line. Okay. So these are the functions that we're going to be filling out in the future over the course of the next several videos. I had that progress matrix in Act 1, and I will have another project. That's suddenly a hard word to say. I will have another progress matrix for Act 2. In addition to basic triangles, which we're going to be checking each of these shapes against in Act 2, we're also going to have, as I think I mentioned earlier, meshes composed of a list of triangles. So this version of the project's matrix is going to have cells for both triangles and triangle meshes. And we'll get to each of those things in due time. So there's a couple other helpful functions that I'll be wanting. One is going to be, and I mentioned this one a minute ago, static get normal. That's going to be a function. There's also going to be static method. I'm suddenly messing up my terminology. I think I was fairly consistent calling them methods in Act 1. And I need to get back in the habit of that in Act 2. There's also going to be nearest point. It's going to be a function. And this is going to take a vec3 as an input. And that's going to find the nearest point on the triangle to the vector3 that was specified. We will be filling that in today. There's also going to be static get plane, which is going to be a function that we're going to be getting into. So first, the first thing that I'm going to do, get normal. If you've ever used a 3D modeling tool like Blender or any of the other 3D modeling tools out there, the surface normals for each triangle will be set more or less automatically by the 3D modeling software. And you generally, if you're working with 3D models, don't have to worry about calculating the normals for each triangle yourself, whether that's a flat normal for the triangle or a smooth normal for each vertex. For the purposes of 3D collisions, we're going to be calculating the normals for triangles ourselves. Calculating the surface normal for a triangle is actually fairly straightforward. Triangle surface normals are just the vector that's pointing perpendicularly out of the surface of the triangle. And we have a handy tool for figuring out a vector that is perpendicular to two other vectors, and that is the cross product. And you would think I would have this memorized by now, considering how many times I've done it, but I'm consulting my notes anyway, just to be sure. First, I'm going to say var diff AB is going to be self.b.sub self.a. Secondly, var diff AC is going to be self.c.sub self.a. These two vectors are going to represent the direction from point A to point B and from point A to point C. And we are going to, we have these two vectors, we are going to generate the surface normal by calculating a little cross product. Return diff AB dot cross diff AC. And this vector is not guaranteed to be normalized, so we're going to normalize it. This function can fail if, for example, all three of the points composing the triangle are the same, because then you won't be able to really calculate a cross product for that. You'll have the zero vector, and then when you try to normalize the zero vector, bad things will happen. but we're going to assume that when you create a triangle like this, you are not going to have a triangle with 0 surface area. I may go into more depth about how this works. I do want to make videos in the future about generating surface normals, both flat and smooth for 3D models that you may generate in real time, but that's another story for another time. Next, nearest point. This is going to actually be a little bit more involved. This is going to actually depend on the getPlane method, so I guess it'll make sense to work on that one first. Triangles, a handy property of triangles is that all 3 of the points that compose a triangle, any 3 points that you can imagine, are all going to be coplanar. There is, for any triangle that is ever going to exist, you will be able to create a plane that runs through each of those points. And that is going to have a few applications when it comes to 3D collision checks with triangles. For those of you watching this who are still in high school, the next time one of your classmates gets up and says something to the effect of, "Who needs math? I'm never going to need any of this in real life. Who cares about planes and geometries and all that weird stuff?" You can officially get up and tell them that you've used geometry in real life and that they should be quiet. So planes are defined by a surface normal and a distance from the origin. The surface normal the surface normal of the triangle we have var norm is going to equal self.get normal. I'm suddenly losing track of my keyboard. That is the method that we just defined a minute ago. As for the distance to the origin, let's say var dist is going to equal, and a handy thing that you can do with surface normals and dot products is norm dot against self dot a. If you take the surface normal of this triangle and if you take the dot product of that against one of the points of the triangle, against point A, in this case, where am I? Page up, page down. If you take the normal and dot product that against self dot a, you're going to get the distance from the origin. Handy little property of math. And as for the plane that we're building, we can say return new call plane. And that is going to take norm as its normal and dist as its distance. And this is going to be getting a plane from a triangle. Next, let us actually do nearest point now. So I'm going to start out with the nearest point function by saying var plane is going to equal self.getPlane. Again, that's the function that we just defined up here. The next thing that we're going to do is we're going to find the nearest point between the input point, the input vector 3, and the plane. So we can say var nearest to plane is going to be plane dot... Was it nearest point? Nearest point? Pretty sure I called it nearest point. I'm using the right terminology here, right? Alright, it is nearest point. So we can start off by getting the nearest point to the plane that runs through each of the points on the triangle. Now, if this nearest point to the plane is already inside the triangle, then that's just it. That's our nearest point. The nearest point between this vector 3 and the triangle is going to be the vector 3 itself. And we don't need to do any further work. And I'm going to be doing a tiny bit of sequence breaking here and saying, we can say if self.checkPoint, and the point that we're going to pass it is just going to be a call point composed of nearest to plane, because each of the shape checking methods, including checkpoint, expects to see a one of the collision shape wrappers. So we're going to take that vector 3 and we're going to wrap it inside a call point.
Hey.
Anyway, if this point is already inside the triangle, then we're just going to return nearest to plane. Triangle checkpoint has yet to be implemented. That's this method up here. We will be getting to that in the next video. But since I do not need triangle's nearest point method implemented for anything that I want to do in the rest of this video, then I think this is an okay concession to make. Next, if the point nearest to the plane is not already inside the triangle, there is something else that we can do, and that is we can break the triangle into 3 lines, which represent the edges, and we can say new call line. This is going to take a starting point and an ending point, and we're going to do this 3 times. One of them is going to be a line from triangles self.a to self.b. Another one is going to be a call line between self.b and self.c. And the third is going to be a new call line between self.c and self.a. If the nearest point is not already inside the triangle, we can figure out the nearest point to the triangle by figuring out the nearest point to any of its edges. represented by a line segment. Let me give these names. Let's call this one var line AB. It's going to be that. Var line BC is going to be that. And var line CA is going to be that. This probably is going to look very, very familiar to anyone who's worked with triangles in geometry, trigonometry, or both. I hope nobody has been too traumatized by this sort of thing from school, because we are going to be doing a lot in the coming videos with this sort of notation, line A, B, and such. Anyway, next, as I said, we can figure out the nearest point to each of these lines, so we can say var nearest to AB is going to be line AB dot nearest point. The input vector, the input point, we can do this 3 more times. We are going to have line BC and line CA, and we're going to use the appropriate line segment in each of these cases respectively. Next, we're going to figure out the distance between each of these nearest points and the lines, and the nearest point to the triangle is going to be the overall closest one of these. So we can say var dist AB is going to be vec3 dot distance 2 nearest to AB. Going to do this again 3 times, dist BC and dist CA. And we're going to be checking the distance to the nearest point to line AB, the nearest point to line BC, and the nearest point to line CA. Okay, and then if dist AB is less than dist BC and dist AB is less than dist CA, then this is going to mean that the nearest to AB point is going to be the nearest point to the triangle. Next, if dist BC is less than dist CA, and I believe at this point this can be proven redundant, but I'm also going to say dist BC is less than dist AB, just so that this if statement looks like the one above it. But I believe this this part of the expression here is redundant. Not going to spend time trying to mathematically prove that. Anyway, we can return nearest to BC, and if all else fails, if neither of these points are the nearest to the triangle, then what's left is nearest to CA as our nearest point to the triangle. Okay, that was a bit longer than the previous 2 methods that I implemented, but it's going to be coming in useful for some things in the next coming videos. If you remember the point and sphere checks from Act 1, you probably have a pretty good idea of what this is going to be used for. But I think that's going to do it for now. We have defined a triangle, we have defined the surface normal of the triangle, the plane of the triangle, and the nearest point to the triangle. Actually, while I'm here, because it would be a shame if I had to do this, if I forgot to do this now and had to do it later. In the call test triangle, self.data, we can assign this a value of new call triangle, and the A, B, and C points are going to be P1, P2, and P3. It's semi-common for people to refer to triangles in terms of both A, B, and C points and P1, P2, P3. I'm going with A, B, C as my 3 points in the triangle, mostly so that I can do things like saying like line AB nearest to BC, that sort of thing, because that's a little bit less awkward than saying like line P1, P2, at least in my opinion. I guess something like line 1, 2 would be just as concise. Anyway, this is going to be defining the collision data for this test triangle, and just for good measure, instead of hard coding nx, ny, and nz to be 0, 0, and 1, we can actually get the triangle's normal from the getNormal method, and we can say nx is going to be norm.x, ny is going to be norm.y, and z is going to be norm.z. And that way, if later on when we generate triangles that are not just lying flat on the ground, then we can calculate the surface normals like this. And in fact, I'm just going to run this now. If I were to generate some triangles, let me zoom in. That's out. Let me zoom in. If I were to generate some triangles, Okay, our surface normal is still looking good. It's still pointing straight up. The top is being fully illuminated. And if I were to randomly generate a z-coordinate of random range between, let's say, -20 and 20, then the surface normal should be correctly calculated, no matter how the triangle is oriented. And let's see, let me find one that's a decent shape. All right, there we go. So this triangle is decently big. We can get a good look at it. It's fully lit, and we can see that the surface normal is pointing in the right direction. It's more or less head on to the light source. If I were to generate one that's lying a little bit more turned away from the light source, we can see it'll be dark. It's maybe not what we want, but it's maybe real quick. Let me go into the shader and bump up the minimum light value, so that we can at least see a little bit of the unshaded sides of triangles. Okay, we're pointing the opposite way from the light source now, and we're still semi-lit, just not in direct sunlight. Okay, let me make this a GitHub commit. Let me actually make this several GitHub commits. First, we're going to define the triangle shape. And then we can, I'm just going to say I updated the demo a little bit. Okay, so with that, I hope you all found that useful. We're going to be doing something with actual collisions in the next video. I am going to tag and create a release. I've been tagging releases, right? It looks like I have been. This is going to be 0.9. I'll bump the number up to 1.0 probably at the end of Act 2. I won't be continuing. I won't start Act 2 off with 1.0 because I feel like we're still not really complete yet. But I think once we have a triangle hierarchy, then I'll officially call that 1.0. Anyway, to create that tag, I will create a release on tag 0.9 pre-release. So if you want the code for this, look for this GitHub repository down in the video description. Specifically, if you're looking for what I did today, look for the 0.9 release. I have a Patreon, so if you want to contribute towards these videos being made, look for the links to that in all the usual places. Otherwise, I try to post about 2 game dev videos a week, one tutorial such as this, and one Let's Make a Tower Defense game. I hope you all find this useful, and I will see you all later. Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games. Welcome back to 3D Collisions in GameMaker. Today we're dealing with triangles. We are going to figure out if a triangle is intersecting with a point or if a triangle is intersecting with a sphere. If I have time, I'll go farther than that today, but I'm only anticipating to get points and spheres done today. So first, let me adopt another design pattern that I made use of in Act 1 of the series, and inside triangles check point method, I'm just going to flip that on its head and turn that into return points.check triangle self. And in triangles check sphere method, I'm going to also turn this on its head and return sphere.check triangle. And this is just going to make it so that we don't have to implement the same thing in both triangles check point method and in the points check triangle method. One is just going to refer to the other. So, I like to think that the method for checking to see if a point is contained within a triangle is actually fairly clever. It's just one of those things that I'm glad that there are smart people out there to figure out so that I don't have to, because I would not have thought of this. I would probably have tried to do something a lot more complicated and a lot less efficient. So we have a triangle, and a triangle is composed of 3 points, which are all coplanar, as I said in the last video. That means all 3 points of the triangle lie on the same plane. And if you take a 4th point, if you take the point that we're trying to check to see if it is contained within the triangle, and if you try to construct a pyramid out of that point, you're going to find yourself with 3 more triangles. Importantly, each of those triangles representing the slopes of the pyramid, the walls of the pyramid, if you will, those all have a surface normal, as does the original triangle, as do all triangles. And if the surface normals of those 3 new triangles are all the same, you know that the point is lying flat on the triangle, because the only way that you would have the surface normals of the three new triangles all pointing in the same direction would be if the point was lying flat on the triangle. if it was above the triangle or behind it or somewhere else off in space, the surface normals of the three walls would be pointing in different directions. And I personally think that's rather clever.
Hey.
I went into my research for this series not having any idea how this was going to be worked out. I think the solution is rather elegant. So to get started, I'm going to say var PA is going to be triangle PA, I said. It's going to be triangle dot A dot sub self dot position. Var PB is going to be triangle dot B dot sub self dot position. Var PC is going to be triangle dot C dot sub self dot position. We are just subtracting the points that we're checking against the triangle from the position of each of the three vertices. This is going to transform the coordinate space of the triangle from whatever world space it exists in to coordinate space relative to the point. You could technically also say our PP is going to be equal to self dot position dot sub self dot POSITION. I'm really losing my keyboard today. But as the eagle-eyed observers among you may realize that this is just going to be a zero vector because anything minus itself is zero. So we don't have to bother with that, which is probably honestly a good thing, because if I say the word PP too many times in a video, I know I'm going to get some weird comments that don't have anything to do with math. Anyway, we are going to generate the surface normals of each of the three triangles. This is going to look a lot like the get normal method inside the triangle shape. We're just going to be finding the cross product of one side versus another and normalizing that, and that is going to be a surface normal. So if I were to scroll back up here to points check triangle, we can say var norm, and I'm going to call this PBC is going to be PB.cross product against PC, and we're going to normalize that so that it has a unit length of 1. Next, var norm PCA is going to be PC.cross PA. Normalize that. And lastly, var norm PAB. It's going to be PA.cross PB. Normalize that. I told you that we were going to be seeing a lot of this this ABC triangle notation in this in Act 2. Next, let's compare the dot products. So again, if all three of these normal vectors are all facing the same way, then we know that the point is on the triangle, and we can say if norm P, let's say PBC dot dot against norm PCA. If this is less than 1, so remember, a dot product of 1 is going to mean that the two vectors are pointing in the same direction. Two normalized vectors are pointing in the same direction. So if the dot product of BC against the BC triangle versus the CA triangle is less than 1, then we know those normals are pointing in a different direction from each other. We can say return false. The point is not inside the triangle. Next, we have another side. So if norm PBC dot PBC, was it? Yeah. Why is that not highlighting? There it goes. GameMaker's just taking its time today. Dot norm PAB is less than 1. Same deal. Then we know that the point does not lie within the triangle. And if neither of these returns false, if neither of these conditions are true, if PBC dot PCA equals 1 and PBC dot PAB equals 1, then the point is contained within the triangle, and we can return true. And that is checking to see whether a point is inside the triangle. So I've updated the tests a little bit. For now, to make it easier to check the triangle against the point, I am generating the triangle with its z-coordinate of 0 again, so that it's lying flat on the ground. And that's just going to make it actually easier for me to put the point in a position where it's intersecting the triangle. And I've also added a little bit of code so that we can actually move the triangle around, and also so that it's drawn in the correct location when it's moved around. So that'll be a little bit different from the test project at the end of the last video. In any case, let me run the game, and I'm going to zoom in, create myself a triangle. We can see that the triangle is overlapping the point. The point is contained within the triangle. If I were to move the triangle around, we can see where it starts and stops intersecting. If I were to move it down, we can see that the triangle is not containing the point. If I move it up, we can see that the triangle is also not containing the point. If I try to move it back to the origin, we can get them overlapping again. Okay, triangles can intersect points. That's great. So if I were to go back and implement check triangle for the collision sphere, if you remember a joke that I beat into the ground in Act 1, you probably can guess what the overlap test for a sphere and a triangle is going to look like. And I'll give you a hint. Spheres are just really big points. And if you think that I'm just going to copy and paste the, for example, the check axis line bounding box against the sphere code and substitute all of the relevant values, then you would be correct. I'm going to say check triangle is going to equal a function which takes a triangle as an input. It gets the nearest point to that triangle, which we implemented last time. It is going to get the distance to that nearest point, and it is going to return true or false based on whether or not the distance to that point is less than or equal to the sphere's radius. And this should be the moment of truth to make sure that I implemented the nearest point method for triangles correctly. I believe I did. I looked over that again after the end of the last recording, so let me run the game, and we're going to be creating ourselves 1, a sphere, and 2, a triangle, and 3, something is going to crash. Points.check triangle, line 300. Did I misspell something? That should be in the nearest point method that I wrote, line 300. Oh, you know what? This needs to be a new call point. Ha! Okay, wow, that's possibly the dumbest mistake I could have made when I typed this out. Anyway, let's try that again. That should inform us whether or not a sphere is contained within a triangle or a triangle is contained within a sphere, one or the other. So we can see that the shapes are overlapping. When they're like this, I can move the triangle around. We have the shapes barely intersecting each other here. There's that Pinocchio nose, which is just the raycast hit location. We can see, if I were to zoom out a little bit, if I were to move off to the left, the triangle is no longer intersecting the sphere. If I were to move off to the right and see if I can move the camera in a way so that I can actually see that, the triangle is no longer intersecting the sphere. Up and down. I've gotten my directions all kinds of backwards today. You are still intersecting, no longer intersecting. At the top, no longer intersecting. So we've implemented triangles and spheres. Okay. Let's see. That is worthy of a git commit. I should probably break this up into points and triangles and spheres and triangles, but they're both pretty simple. So points and spheres and triangles. So, this video hasn't been going on for too long, but it's gone on for long enough that I don't want to try and combine anything else into it, because that would probably start to run a little long in the duration. So, if you want the code for this, look for the GitHub repository in the video description. This should be the 0.10 release. I'm not going to create the release itself on recording today, as I did the last time. I have a Patreon, so if you want to contribute towards these videos being made, there are links to that in all the usual places. Otherwise, I try to post about 2 game dev videos a week. One tutorial like this one, and one Let's Make a Tower Defense game. I hope you all found that useful, and I will see you all later. Okay, hello all you crazy people out there. My name is Michael, I like wizards and dragons and making games, and today we're going to be dealing with the SAT. So the SAT is a tool that is going to be making our lives considerably easier in the coming weeks. And if you're a North American high school student, this is approximately where you should be starting to become suspicious that if you clicked on this video thinking you were going to find information about the Scholastic Aptitude Test, then you are indeed in the wrong place. Let's talk about the separated axis theorem. So today we're going to be taking a step back from triangles and 3D collisions, and we're instead going to be talking a little bit more theory when it comes to 3D collisions. So the separated axis theorem is a test for figuring out if 2 arbitrary shapes, if they intersect, and it does so by trying to find a line that you can draw between them. To illustrate the point, I'm going to be drawing up a few diagrams in 2D space. It also works in 3D space and in higher dimensional spaces. But if you have 2 shapes, let's say these 2 rectangles, and if you are able to find a line that you can draw between them, then that is one axis of separation, and you know that these 2 shapes are not intersecting. And this is a fairly solid generic test that you can use for a bunch of different collision shapes in 3D space. Note that this will only work for shapes that are convex, or at the very least it'll only work for shapes that are not concave. if you have a shape that's shaped something like this, then it is possible for it to be intersecting with another shape without any possible axes of separation being found between them. But regardless, this should pave the way for a number of potential 3D collision tests between different shapes, which might otherwise be considerably more work to evaluate. So I'm going to start by defining a few more helper functions. I guess I could put it inside the call helper functions code file, but instead I think I will put code related to the separated axis theorem in its own code file. So I'm going to call this call SAT stuff. And this is going to be a couple different functions. The first one that I'm going to define is going to be function, I'm going to call it call interval. And it's going to take two parameters, val min and val max. It's going to be a constructor. And this is essentially just going to create a struct which takes these two input parameters, the val min and the val max, and it's going to save them to instance variables of itself, self.val max equals val max. I would love to be able to just call these two values min and max, but min and max are reserved functions of GameMaker, and I am not allowed to name variables that, unfortunately. So we'll just be going with val min and val max. So this is a simple data structure which is going to represent an interval, as the name implies, on a single axis. So it is going to represent a minimum point on that axis as well as a maximum point. We'll see an example of this in practice soon enough. Next, let us go into the axis-aligned bounding box class down here, and let us re-implement a collision check which we have already implemented, using the SAT instead of using just the analytical method that we were using earlier. So I'm going to add at the bottom some code. I'm going to add a method static check ab SAT, and we've reached the point where none of these things sound like words anymore. This is going to be a function which takes an ab, which takes an axis-aligned bounding box, and it's going to return a result. And I'm going to just temporarily comment out all of this up here. Everything that's already in the axis-aligned bounding box check ab method, and we're just going to return self.check ab AABB SAT with the input parameter. And we are going to re-implement this. Let's just return false for now. If we run the game now, and if I were to pit two axis-aligned bounding boxes against each other, we would see that we are no longer going to be detecting collision with either of these shapes, even though we totally should be. Okay, we're going to re-implement that. That is going to be largely the focus of today's video to illustrate what you can do with the separated axis theorem. So let's start with the axes. So the separated axis theorem is going to test for possible axes of separation between two shapes, as I said. This tends to be easiest if you have two axis-aligned bounding boxes, if the two shapes in question are axis-aligned bounding boxes, because you already know that there are three potential axes of separation between these, and they're never going to change, and they're always going to be the same. And if you were to try to do this with other, more complicated shapes, then you would have far more axes that you can test, which is going to quickly add a lot to the amount of code that you have to write. And the three axes that you can possibly draw between two axis-aligned bounding boxes are going to be, I'm going to create myself a variable var axes. And those are going to be a new vector 3, and the first one is going to contain a 1 on the x-axis, a 0 on the y-axis, and a 0 on the z-axis. The second one is going to be a vector 3 containing a 0 on the x-axis, a 1 on the y-axis, and a 0 on the z-axis, and you can probably see where this is going. New vector 3, 0 on the x-axis, 0 on the y-axis, and 1 on the z-axis. And these are the potential three axes that you might be able to test between two axis-aligned bounding boxes. They're not called axis-aligned for nothing. Next, we're going to loop through each of these axes for var I equals 0, I is less than 3, I plus plus, and we are going to see if there is any intersection between these shapes on these two axes. Again, here's a visual representation of two rectangles in 2D space. If we were to check the x-axis for overlap, we would, for example, draw the x-axis on this diagram, and we would get the interval between the minimum and the maximum point of the first rectangle on the x-axis, and we will get the minimum between the first and the second point on the x-axis on the second rectangle. And if those two intervals overlap, that means that we do not have an axis of separation. If we were to test it again on the y-axis, we would do the same thing using the minimum and maximum intervals on the y-axis for each of these two rectangles and check to see if they overlap or not. If there are no free axes, then we know that the shapes are intersecting. Otherwise, we can write a little bit of code. If not, I'm going to define a new function in a minute, call overlap axis. This is a function that I'm going to write momentarily. It's going to take two parameters. It's going to take three parameters, I'm sorry. The first parameter is going to be self, which is going to be an axis-aligned bounding box. The second parameter is going to be the one that we're checking against, and the third parameter is going to be the axis in question. So axis, axes, plural, at index I. And like I said, if no overlap is found on this axis, we know that there is an axis of separation between these two shapes. We can return false. Otherwise, if there is an overlap on each of the three axes, we know that there is a collision. We can return true. So let's get to the overlap on axis function. And this is going to go in the SAT stuff script file. And like I said, this is going to take three parameters: function, call, overlap axis. The first axis is going to just be shape 1. The second parameter is going to be shape 2. And the third parameter is going to be the axis that we're testing. This is just going to be a regular function which returns a value. It's not going to be a constructor. So call overlap axis is a function that's going to just return a value. It's not going to be a constructor. This is also going to just work the same for pretty much every single possible combination of shapes, so I don't have to do any fancy, I don't have to implement this separately for any possible combination of shapes that you might want to test for axes of overlap. And to do so, we are going to find the interval that both shape 1 and shape 2 take up on the specified axis. And I'm going to say var A is going to be the interval on the axis of shape 1, and var B is going to be the interval on the axis of shape 2. And we are going to implement a few new functions, specifically a function to return the interval that each shape takes up on the axis. So I'm going to say shape1.get interval. And this is going to take a single parameter. Again, I'm going to implement this soon enough. B is going to be the same thing, but shape2.get interval on the axis. And then to see if the two intervals overlap, you can probably reason through this visually. Here's the diagram again, if it helps. We can return b.val min is less than or equal to a.val max, and I'll put these in parentheses just for safety. And a.val min is less than or equal to b.val max. And there's a space where there shouldn't be in this less than or equal to. So this is just going to check to see if the minimum value of one is less than or equal to the maximum value of the other, or vice versa. If either of the intervals overlap, then this is going to return true. If neither of these intervals overlap, then it is going to return false. So going back to the shape, I'm going to need to now define static get interval, and that's going to be a function which takes an axis as the parameter. Fair warning, this isn't going to be complicated code, but it is going to involve a little bit of typing. We are going to find the minimum and maximum points for this axis-aligned bounding box on each axis. So let's start with var p min is going to be equal to self.get min, and var p max equals self.get max. And these are going to be the minimum and maximum points, vector 3s in 3D space of this axis-aligned bounding box. Next, let us construct an array that is going to just contain each of the 8 points which compose the axis-aligned bounding box. A rectangular prism, as you may remember from geometry class, has 8 points, and we're going to build them all. So I'm going to say var vertices equals an array, which is going to be composed of several things. This is going to be an array of vectors, so new vector 3. The first is going to be pmin.x, pmin.y, pmin.z, and there are going to be 7 more. 1 for each point. We're going to have, let's say, p min x, min y, min z, min x, min y, max z, min x, max y, min z, min x, max y, max z, max x, min y, min z, max x, min y, max z, max x, max y, min z, max x, max y, max z. And that's another thing that I've now said so many times it doesn't sound like a word anymore. So this is an array containing vector 3's representing each of the 8 vertices on this axis-aligned bounding box. Next, we need to figure out the minimum and maximum values of each of these. If you just had a known axis that you were testing for example, the x-axis, or if you knew you were testing for the y-axis or whatever, then you would really be able to just get like get min.x and get max.x, and that would be your interval. But since we're testing for an arbitrary axis, we're just going to loop through all of these points and get the minimum and maximum values of those points on each axis. We can do that by saying var I min is going to be equal to, let's say, axis dot product against the 0th vertex, and we can say var I max is going to be equal to the axis dot product against, again, the 0th vertex. If you want, you can simplify this. You can just say I max is going to be equal to initially I min. What is the shortcut for opening up the start page in GameMaker? Because like I keep doing it by accident, and I have no idea how I keep doing it by accident, and I keep doing it. And if I knew what the short key was, I would just go into preferences and turn it off, but whatever. Anyway, after this, we can loop through for var I is going to equal to 1, I is less than 8, I plus plus. We can loop through the rest of the array, and we can say var dot is going to equal axis dot against vertices index I.
Hey.
And we can say I min is going to be equal to the minimum value of the existing I min, the existing minimum interval, or you can, or it's going to be the minimum of that, or the dot product. And I max is going to be the maximum I max, or the dot product. And this is just going to, this loop is just figuring out the minimum and maximum value of the axis dot product against each of these vertices. And then when we're done, we have our final I min and I max on whatever axis we specify, and we can return new call interval with the minimum and maximum values being set to the minimum and maximum that we calculated in this getInterval method. So that should be everything. Is there anything left that I need to implement? In the overlap axis method, we've implemented getInterval. In the check ab method, check ab sit, we've implemented overlap axis. This should work. If I were to run the demo program now, and if I were to spawn a couple axis aligned bounding boxes, we have the shapes are overlapping now. If I were to move one outside the other, beautiful. Okay, so as soon as the first axis aligned bounding box leaves the second, a collision is no longer detected. Same is true on the other side. The same is not true on the other side. All right, I must have did I like miss a greater than or less than or something somewhere? Oh, ha. A.val min is less than A.val max. That should be a B. Right? My notes? They agree? Okay, my notes want them the other way around. E.val min is less than A.val max. That works. As long as they both get calculated, it's fine. Let's see. Axis line bounding box and an axis line bounding box. Let's see if they both work on all axes this time. At the left, good. At the right, good. At the top, at the bottom, on the z-axis, at the top and at the bottom. Okay, this works. We have a separated axis theorem test for intersection between two axis line bounding boxes. That's fine. Both this and the version of the AABB overlap test that we've already written, they both work. This is, I believe, slightly more computationally expensive because it does a lot of jumping through functions and doing a lot of method calls. Whereas the version that we had originally it basically did the same thing. It basically tested for the three axes overlapping, but it did it in far less code. Because, like I said earlier, we know the three axes that an axis-aligned bounding box may be able to test, and we can just make some assumptions based on that, and we can not have to jump through a lot of hoops involving like redundantly calculating the interval a bunch of times. So I think for the purposes of this this demo, if anyone wants to use this code, I'm going to leave the initial version of check ab as the version that's actually being used, and check ab SAT. I'll leave the code here as a point of interest. But, like, if someone wants a simple example of the separated axis theorem, I'll leave the code here, but we won't really be making use of it because it does a lot more calculations than it really has to. Okay. We will be seeing more of the separated axis theorem in the coming days. It will be coming in handy for some of the other shapes that we're testing for intersection against. I believe it is relied heavily upon when you start getting to oblique bounding boxes, which are basically axis-aligned bounding boxes, but not axis-aligned. Unfortunately, when I was doing my research for these videos, I found a lot of stuff on the internet about the separated axis theorem that was written in heavy math jargon, and it was hard to parse without like sitting down with a pen and paper and working your way through it. And I don't know exactly why that is, because it's not that complicated once you find someone who's willing to actually try to explain it in English, which I hope I've been able to do here for most of you. But regardless, I like this version of the SAT a lot better than the Scholastic Aptitude Test myself. Anyway, I am going to commit this to source control. Let's just call this a bunch of SAT stuff. It's possibly the worst commit message I've ever written. That was only one commit in this entire video. That's probably not like a great practice, but regardless, this is going to be the 0.11 release. Check for the GitHub repository in the description of this video. I have a Patreon, so if you want to contribute towards these videos being made, there'll be links to that in all the usual places. Otherwise, I try to post about 2 game dev videos a week, one of these and one Let's Make a Tower Defense game. I hope you all found that useful. Next time, I'm going to be implementing a few more helper functions before I get on to triangle collisions, and I will see you all later. Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games. Welcome back to 3D Collisions in GameMaker. So far in Act 2, we've defined some simple things with triangles. We've defined collisions with triangles and spheres. That's pretty easy. We've also talked about the separated axis theorem, which is a tool for helping us to find axes of separation between arbitrary shapes to see if they intersect or not. And today we're going to be writing a few more helper functions, which are going to come in handy in various places in the coming weeks. That shouldn't take too long, and assuming it doesn't, I'll also be getting on to checking for collisions between triangles and axis-aligned bounding boxes, as well as triangles and planes, the latter being somewhat simpler. So the first additional function we're going to implement is going to be a method belonging to the vector3 class, and this is going to be a new method, which I have not really mentioned so far, but it can come in handy, and that is going to be static project. And that is going to be a function which takes an argument of a direction. This is the direction parameter for, come on, help. There we go. The direction parameter for the projection function method, whatever, is going to not be just a degree value or a radian value or anything like that, but it's going to be another vector itself. If we project one vector onto another, we are essentially going to be getting the magnitude of that vector in the direction of the second vector. I'll have a diagram of what I mean on the screen right now. Hopefully it's comprehensible, at least on the standards of linear algebra anyway. So let's start off by saying var dot is going to be the dot product of ourselves, of our own vector, and we're going to dot ourselves against the direction. The magnitude is going to be the magnitude of the direction. And to project our vector onto another, we are simply going to return direction dot multiply the dot product divided by the magnitude squared. As a bit of an aside, I have elected to not do this wherever it might come up, but in some places, for optimization purposes, because it's slightly more efficient to calculate, you might see magnitude squared defined by a vector dot product against itself. And if you recall the way that the dot product works, it's the product of the x components of the two vectors multiplied by the product of the y components of the two vectors multiplied by the products of the two z components. If both vectors are the same, that's basically the value that's under the radical in the distance formula, and you can use that to get the magnitude of a vector squared without having to do a square root, which is, it's one of those things that, yes, it's technically more expensive, but since GML is a very, very slow language anyway, a single square root here and there is probably not going to be where the slowdown in your code comes in, but I just thought it might be worth mentioning that. Anyway, another helper function that I would like to implement is going to be, where is the plane? The plane is just this one. Okay, I'm right here. We are going to implement something similar to the dot product for a plane, and that is going to be, I don't know if this actually has a name. I've just seen it called on the internet and elsewhere the plane equation, which makes it sound like cryptic and arcane, but all this really is it functions a lot like the dot product in that it returns a value between 0 and 1 to describe where a point is in relation to a plane. I'm going to say this is going to be a function, and it's going to take a vec3 as an input. If any of you are interested in astronomy or space travel, you may have heard of something called the rocket equation, and rest assured, the plane equation is quite a bit simpler than the rocket equation. That's an aerospace joke, I'm really sorry. So the plane equation actually functions quite a bit like the dot product in that it will take a vector, a point in space, and compare it to, instead of another vector, we'll compare it to a plane. And the plane equation will return a value of +1, or positive something anyway, if the vector is in front of the plane. It will return a value of 0 if the vector lies on the plane, and it will return a value of something negative if the vector is behind the plane. Again, that's like the dot product. If the point lies on the plane, then its plane equation value is going to be 0. If the point lies in front of the plane, then its plane equation value is going to be some positive number. It's going to be 1 or so. And if the point lies behind the plane in the opposite direction of the plane's normal, then its plane equation value is going to be -1. You can probably imagine how this is going to work as well. In fact, if we start with the dot product, we can say var dot is going to equal vec3 dot against self dot normal. We're going to be taking the dot product of that vector against the plane's normal, and we're simply going to return dot minus self dot distance. So we're going to take the relation between the vector and the plane's normal, and we're going to subtract out the plane's distance from the origin, and that is going to give us the plane equation value. So again, that's a lot like the dot product, the regular dot product. I guess I might as well, this is something I might leave a comment for. And that's the plane equation. Okay, that is the plane equation. Let us move on to triangles, and we have something called a barycentric coordinate, which is going to be becoming relevant in, I think, several videos from now. And we would like a method which can return a barycentric coordinate of a point in space on a triangle. So barycentric coordinates aren't really something where the name gives away what it does, at least not in an obvious way. So a barycentric coordinate is a way of measuring a point's position relative to the 3 vertices of a triangle. Let me type out. I guess I'll call this, I'll call this barycentric just to keep things simple. It's going to be a function, and it's going to take a vector 3 as an input. And and the barycentric coordinate is going to be a vector 3 itself, but instead of representing points in space, instead of representing an XYZ position in world space, the 3 components of the barycentric coordinate are going to measure how close the input vector 3 is to each of the vertices that compose the triangle A, B, and C. For example, if the input vector 3 is located on point A, then its barycentric coordinate is going to be 1, 0, 0. If the input vector 3 is located on point B, then its barycentric coordinate is going to be 0, 1, 0. If the vector 3 is located on point C, it's going to be 0, 0, 1. And if it's in the middle of the triangle, it'll be around about 0.5 on all three axes. If it's outside the triangle, its barycentric coordinate may be greater than 1 or less than 1 or something like that. I'm not going to be making use of this calculation right now in the immediate future, but farther on down the line I will be using it. So, let us start by doing something that I did in, I believe, the point triangle calculation, and that is going to be var PA is going to be vec3 dot sub self dot A. Var PB is going to be vec3 dot sub self dot B. Var PC is going to be vec3 dot sub self dot C. And as this was the last time we did something like this, this is going to be transforming each of the coordinates of the triangle into coordinate space relative to the input vector, into the input point. Next, let's turn this into lines. Let us say var AB is going to be self.b.sub self.a. So this is going to be a vector from point B to point A, or from point A to point B, depending on your perspective. It's going to be one of the edges of the triangle. Var AC is going to be self.c.sub. I don't really need the parentheses there. Self.a. Let's also, we want these going in both directions. Next, we have our, say, BC is going to be self.c.sub self.b. And let's go the other way for two of these vectors. Let's say our CB is going to be equal to self.b.sub self.c. And our, lastly, CA is going to be self.a.sub self.c. This is going to be 5 values, you may notice. The only one that's really missing, you may observe, is going to be var BA is going to be self.a.sub self.b, but I don't believe we're actually going to need that, so there's no point in calculating a value that we're not going to use. Wasting CPU cycles. Next, we've got the edges. We can say var v is going to be equal to ab.sub ab.project cb. This is unfortunately where my ability to describe what's going on here is going to start falling short a little bit. Honestly, I was kind of struggling to think of ways to describe the projection function itself too. But regardless, when I go to edit this video, I'll try to come up with a way to visually describe what's going on here, because this is definitely a little bit more on the abstract side.
Hey.
Anyway, the value v here is going to represent vector AB projected onto vector CB, so the two sides of the triangle. Next, I'm going to say A is going to equal 1 minus V dot dot against AP, or PA, I'm sorry. And that is going to be, remember, point A relative to the input vector. And we are going to divide by V dot AB. Next, V is going to be redefined as, let me scroll down, bc.sub bc.project AC, and we can say var b is going to equal 1 minus, and this is going to look rather similar to the last block of code, v dot pb divided by v dot bc. And we're going to do this one more time. V is going to be redefined again as ca.sub ca.project on AB, and var c is going to equal 1 minus v dot pc divided by v dot ca. And here, A, B, and C are going to be our barycentric coordinates. Now all we have to do is return a new vector 3 composed of A, B, and C. And that is our barycentric coordinate. That'll be something that I'll be forgetting about for a couple videos and then coming back to. And then I'm sure by the time we get there, I'll be glad that I did it now and I won't have to do it again in the future. Okay, how long have I been recording? I've been recording for 19 minutes. I have all the pieces in place for axis-aligned bounding box versus triangles and planes versus triangles. Do I want to keep going? How quickly do I think I can get this done is the important question. Okay, you know what? Axis align bounding box and triangle is just going to be a little bit of separating axis theorem, which I shouldn't take too long to explain because that was what the entire last video was about. And planes versus triangle is, honestly, I think planes versus triangle is a lot of fun. And I realize how nerdy that sounds, but regardless, we'll do it. So let me make a commit. This is going to be some extra helper functions. And I guess, should I rename this branch? Can I rename this branch? Because it's no longer just going to be the helper functions. It's also going to be, I can rename. Helper functions and ab and plane. All right. That's what the week 12 branch is going to be named now. So let's do the SAT. In the AB collision shape in check triangle, first let us define the edges of said triangle. We've seen this before. I'm going to call it var AB is triangle dot B dot sub triangle dot A. Var BC is going to be triangle dot C dot sub triangle dot B. And var CA is going to be triangle dot A dot sub triangle dot C. So these are the three edges. These are the three vectors representing the three edges of these triangles. Next, we are going to have a few our axes. This is going to be var axes is going to be an array. This is going to be a somewhat longer array of axes of potential separation than we had for AB versus AB. We're going to have the same ones. We're going to have the same normal vectors that we had for the axis line bounding boxes. So we'll start by saying new vector 3, 1, 0, 0, new vector 3, 0, 1, 0, and a new vector 3, 0, 0, 1. That needs to be a 0 up here. So we have the x, y, and z axes of potential separation. We also have, because triangles are more complicated shapes, which may have more potential axes than just two blocks, we're going to have the surface normal of the triangle. You could potentially draw a line between the triangle and the axis line bounding box on its surface normal. So that's going to be triangle.getNormal. And we also have the cross products of each of these normals, each of the x, y, and z normals against each of the edges of the triangle. And you know what I'm actually going to do is I'm actually going to, instead of typing out the vector 3, the vector 3s representing the axes over and over again, I'm going to define them down here as var nx, var ny, and var nz. To this day, every time I see nx, I think of the Nintendo Switch's codename. And in the axes array, we're going to be saying nx, ny, and nz, and we're not going to be evaluating vectors of these of this exact value every single time. So as I said, the each of these three vectors crossed against each of the three edges of the triangle, so that's going to be 9 more potential axes of separation. So this is going to be a total of 13 items in this array of axes. So we have nx dot cross edge AB. Did I say cross or dot? And I'm just going to call that AB because that's, in my notes I called it edge AB, but then I decided I don't feel like typing that out over and over again. Anyway, it's going to be nx dot cross product against AB, nx dot cross product against BC, and nx dot cross product against CA. We're going to do this 2 more times for ny like this and nz like this, and this is going to give us 13 axes of separation. And then, much like we did in the SAT version of AB versus AB, we are just going to loop over every one of these axes. Where are we? Up here. And instead of saying for I equals 0, I is less than 3, it's going to be I equals 0, I is less than 13, I plus plus. You could just get the length of the axes array if you want, but it's not like that value is ever going to change here. And we are going to do the same overlap test that we did for call underscore overlap underscore axis for, instead of another AB, it's going to be the triangle. And we will need to implement the get interval method for triangles. And if I scroll down, I didn't already do that, did I? I don't believe I did. I'm pretty sure I did not already do the interval method for triangles, and it looks like I did not. Okay. So as a bit of a refresher, and let me just collapse all these so I don't have to scroll so far. Check line doesn't matter. Check normal we've already done. Get plane we've already done. Get nearest point we've already done. Barycentric we've already done. The entire plane class I can collapse right now. So as a bit of a refresher, for the axis line bounding box, the way we did get interval was by figuring out each of the 3 points of the axis line bounding box, looping over that array, and getting the minimum of the dot product between the axis and said vertex. That was definitely what one might call the most efficient way to do that for an axis line bounding box, because the axis line bounding box has 8 points, 8 vertices that you will need to check. Triangles being simpler shapes which only have 3 vertices. We can get away with doing a little bit less work. I'm going to say static get interval is going to be a function that takes an axis as a parameter. I'm going to call it var I min is going to be the minimum value of, instead of putting all the vertices in a loop and looping over that, putting them in an array rather and looping over the array, I'm going to instead just hard code all these. I'm going to say axis dot dot self dot a, axis dot dot self dot b, and axis dot dot self dot c. The GameMaker's min and max functions can take as many arguments as you want to give them. So you would ordinarily use the min and max functions with just 2 arguments. I'm going to be using the min and max functions with 3 arguments here. If you, for whatever reason, ever needed to do the min and max functions with 4 or 5 or 6 or however many arguments, you should be able to do that. In the book that I've often referenced that I've been using for a lot of my research for this series, Game Physics Cookbook, Gabor Zauer, the author, did actually put the 3 vertices of the triangle in a loop, but and I did it again in an array and loop over an array to get the minimum and maximum values, but I personally think that's a little bit overkill. And in any case, since let's just say C code comes with a little bit less overhead on things like loops than GameMaker code does, and since C and C++ give you some fun things like unions, which you can take advantage of for things like this, and GameMaker language does not, I'm just going to be hard coding the minimum and maximum values in the like this. So we have our min and max values, so we can just return a new call interval, I min, I max, and that should allow us to use the separated axis theorem, and check for triangles for collision against axis-aligned bounding boxes. I believe that's all we need to do. Let me run the game, and I hope this doesn't blow up in my face. The way it did when I tried to show something earlier and I didn't have a new in front of a constructor and things got weird. Let's see, I'm going to ask for a triangle. I'm going to ask for an axis-aligned bounding box, and we do not have a collision between the triangle and the axis-aligned bounding box. Am I, Did I forget in the triangle class to reflect the check ab method? I did. So we're going to say return ab.check triangle. Okay. I had a feeling that was the more likely thing to be going wrong. So we're going to have a triangle versus an ab, and if I were to, it's still not working. Now I gotta go hunting for typos. Oh, wow, okay. You are all laughing right now. At the end of this function, if no separating axis is found, return true. Alright, I was like checking to see if I had like gone cross-eyed writing down A's and B's and C's up here in the body of the function, but nope. I just need to actually return true if no axis of separation is found. Okay, embarrassing code errors all day here. So now we can see that this is indeed working as it should be. The block is overlapping the triangle. If I were to move it out here, the block is no longer overlapping the triangle. If I move it out here, again, left, right, wherever we happen to be, if I were to move it down below the block, we are no longer overlapping. We have an axis of separation that is the basically the x-axis over here. If I were to move it up, same thing. We have an axis of separation. Okay, so that is triangle plane. How long have I been recording today for? This has been going on for 33 minutes. Hopefully that'll be cut down. I know I've spent like 5 minutes checking for typos in the code and not finding any. Next, we're going to do triangles and planes. So first, let me head off one of those embarrassing errors by going into triangles check plane method and turning that on its head. Return plane dot check triangle with ourself. And now we can actually implement triangles and planes. So if I were to go into the, that is the AABB class, in the plane class, if I were to check the triangle. So figuring out if a triangle intersects a plane is fairly easy. We have the plane equation, which is like the dot products, but for a vector and a plane rather than two vectors. And we can use that to figure out which side of the plane any given point is. And if all of the points of a triangle are on the same side of a plane, then there is no intersection between the plane and the triangle. Otherwise, if some points are on different sides of the plane than others, then that means the triangle has to pass through it at some point. Worth noting, by the way, for planes, I will not be implementing getInterval, because getInterval is kind of useless for planes because planes are infinite. And the plane's interval on any given axis is going to be either 0 if the plane is perpendicular to the axis, or it's going to be infinite because the plane is going to just run off infinitely in all directions. And we won't be using any SAT tests between planes and other shapes. At least I'm pretty sure we won't. I'm going to assume that we won't, because the interval for a plane is somewhat meaningless. Anyway, we can figure out which side of the plane all three points of a triangle are on. So we can say, let's say our side A is going to be self.plane equation of triangle.A. We are going to do this 3 times for points A, B, and C on the triangle. Now, there is a bit of a special edge case here. If the triangle lies completely flat on the plane, then you would consider the triangle to be intersecting the plane, but all three of the plane equations of the 3 points are going to be 0. So we can take care of that early on by saying if side A equals 0 and side B equals 0 and side C equals 0, then we can simply return true. Otherwise, if each of these points of the triangle are on the same side of the plane, then their plane equation values will have the same sign. They will either be all positive or all negative. If, let's say, sine of side A is equal to sine. I'm getting sine and side mixed up. Psi of side B, and I have a rogue parentheses there. If the sine of side A equals the sine of side. I really hope I never have to say the word sine or side ever again in my life. Side C. I guess I should just be grateful that I don't have to take the sine of the side. Ugh. If all 3 of the points of the triangle are on the same side of the plane, there is no collision. Return false. Lastly, if the 3 points of the triangle are on different sides of the plane, return true, there is a collision. And that should allow us to have a plane intersect a triangle. I am going to generate a triangle. I am going to, let's say, generate a plane. The shapes are z fighting because they're currently both on the same plane. The plane and the triangle are both in the same distance from the camera, so we have some z fighting going on here. The shapes are overlapping. If I move you around, the shapes are overlapping. If I move you up or down, you are not overlapping. A little bit more of an interesting example would be if I were to go back to giving these test shapes a random z coordinate like this, and then we can actually move these shapes around in 3D space, and we will be able to see where the intersection starts and stops. So there's the plane, there's the triangle. We can see the triangle is currently wedged in the plane. The plane is fighting with a grid. I don't like that. That's annoying. I wish it wouldn't. If I were to move the plane up, or if I were to move the plane up or down, we can see that the overlap begins here and ends here. If I were to rotate the plane and move it backwards or forwards, we can see that the intersection starts here on the sharp edge of the blunt edge of the arrowhead or whatever, and it ends here on the sharp edge. Okay, planes and triangles. So I am going to end this off here. Next time is going to be the big one. This is going to be triangles and triangles. That's going to be a bit much, so I'm just going to make that an entire video all on its own. After that comes raycast with triangles, and then it's time to start dealing with collision meshes, so actual collisions with 3D models instead of just primitive shapes. I know a number of you have expressed interest in doing collisions with terrain in GameMaker. And height maps are actually a bit of a separate thing, based on some assumptions that you may make about them, but that's a story for another day. So I'm going to stop now. If you want the code for this, look in the GitHub repository in the video description. I have a Patreon, so if you want to contribute towards these videos being made, I will definitely appreciate that. Links in all the usual places. You could see your name in the credits, hear yourself shouted out at the end, see a preview of my future plans, that sort of thing. Otherwise, I try to post about 2 game dev videos a week, one of these and one Let's Make a Tower Defense game. I hope you all enjoyed that, and I will see you all later. Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. So I've had a bit of a minor, hopefully, change of plans in the order that these videos are going to come out. I was originally going to do triangles against triangles today, but to make a long story short, I decided that the solution that I had for triangle versus triangle I did not like very much, so I'm going to put that off for another week or so to hopefully give myself time to figure out a better solution. And in the meantime, today I'm going to talk about triangles and lines. So, if I were to run this 3D Collisions demo project, we have the ability to detect some collisions with some 3D objects, such as zoom in. There's the button. Such as the axis line bounding box. I can move my mouse cursor over it. I can cast a ray into it, and we can obtain some information about the location of contact where the ray intersected with the axis line bounding box. Today we're going to do that with triangles. So if I were to give myself a triangle, we do not yet have code to detect raycast hits or line cast hits with a triangle. We're going to do that today. So in the ColShapes code file, in the triangle class, I've collapsed all the rest of them so that we can save a little bit of space. I am going to first look inside check ray. And thanks to some code that we have already written, this is actually going to be pretty simple. So the first thing I'm going to do is I'm going to get the plane that the representing the plane of the triangle. I'm going to call it var plane is going to equal self.getPlane. I'm going to cast a ray into that plane. We can say plane.checkRay. The ray that we are going to check is going to be the one that we are taking as a parameter to the checkRay function of the triangle. So the first one is going to be ray. The second parameter is going to be a plane hit info, a hit information object. This, you might want to make this the hit information object that we're also passing to this triangle, except we actually don't want to, because this will set some of the information of the hit info, and if the ray does not actually collide with the triangle, we don't want that. So I'm going to create myself a separate hit info object. I'm going to call this plane hit info. Is going to be new raycast hit information, and we are going to instead pass this plane hit info to the check ray method of the plane. If the ray does not hit the plane, then we know that there is no collision. We can just return false. So if the ray that you're casting doesn't hit the plane that the triangle lives on, you know by extension that the ray that you're casting also does not hit the triangle itself. That's pretty simple. Next, if the ray does hit the plane, then we need to figure out if the point of contact between the ray and the plane is actually within the triangle. And we can use our friend that we defined not so long ago, the barycentric coordinate, for this purpose. So the barycentric coordinate, just as a refresher, is going to be a different way of looking at the coordinate of a point relative to a triangle. It is going to have a value of 1, 0, 0. If the point is exactly at the first point of the triangle, it is going to have a value of 0, 1, 0. If the point is exactly sitting on the second point of the triangle, and it is going to have a value of 0, 0, 1 if the point is sitting on exactly the third vertex of the triangle. And if it's somewhere in the middle, it'll have coordinates somewhere between 0 and 1. If it is off the triangle in any direction, then it will have a some coordinate that is greater than 1 or less than 0. So what we can do, knowing this, is we can take the point where the ray hits the plane, and we can turn this into a barycentric coordinate. So I'm going to say var result is going to be plane hit info dot point. So that is the exact point in space where the collision between the plane and the ray happens. I am going to turn this into a barycentric coordinate by saying var barycentric. Did I spell that right? B-A-R-Y centric is going to be equal to self dot barycentric, and the parameter that this is going to take is going to be the result. So we've taken this point, we've turned it into a barycentric coordinate with respect to the triangle that we're checking. Now, all we have to do is check to see if the if this barycentric coordinate is within the triangle. Again, we know that if all three of the coordinates on the the coordinates of the barycentric coordinate are within the range of 0 to 1 inclusive, then the point is within the triangle, otherwise it is not. So we can say if barycentric, and I'm going to use 2 parentheses here, barycentric dot x is greater than or equal to 0, and barycentric dot x is less than or equal to 1, close parentheses, and we're going to do the exact same thing for the y. Barycentric dot y is greater than or equal to 0, and barycentric dot y is less than or equal to 1. Lastly, you probably can figure out where this is going to go if barycentric dot z is greater than or equal to 0, and barycentric dot z is less than or equal to 1. If all these conditions are true, if all 6 of these conditions are true, then the barycentric coordinate is within the triangle. Then the point is within the triangle. We can return true. We would likely like to update the original hit info that we passed into the check ray method, so that whatever's calling this code can have the knowledge of where that hit occurred. So we can say hit info dot update. And we can just copy in the information from the plane hit info struct, because that is going to be exactly the same information. Hit info to update plane hit info dot distance. That is an email. I thought I closed my email before I started recording. Apparently I didn't. All right, go away, email. The argument. What arguments does this take? This is distance, shape, point, and the surface normal. Okay, that's what I thought they were. So we can take the distance, which is just going to be plane hit info.distance. We can take the shape, which is going to be our self. We can take, I've already forgotten what the point, which is just going to be result, which is going to be plane hit info.point. And we can take the surface normal, which is going to be plane underscore hit info.normal. You could also use the triangle's normal. It doesn't matter, but since that's already been calculated, there's no real reason to. Where is it exactly? It's this one. There's no reason to have to calculate the triangle's normal all over again. So, if this doesn't happen, then the ray does not intersect the triangle. We can return false. And if I were to run the game now, and if I were to give myself a triangle collision shape, we should be able to see when I have my mouse cursor going into the triangle, we have a raycast. We have the position where the triangle is being hit by the mouse. We have the normal of the triangle, which is just indicated by the second ball that's floating about an inch above the first one. You will notice, and you may have seen this a minute ago when I accidentally turned over the camera, this is only one direction. This only works in one direction because planes detect raycasts in only one direction. And this on top is the back face of the triangle, and if I were to try to raycast into here, no hit would be detected. Only a raycast on the front-facing side of the triangle will be detected. I am not currently planning on going into making the raycast detect collision with the reverse side of the triangle, but if you want to do that, and you made it this far in the series, it shouldn't be too difficult for you to figure out how to, for example, reverse the triangle by reversing the order of its vertices and checking that for collision instead. Naturally, this will be twice as expensive as checking the original triangle with the raycast, but okay, let's see. I did not mean to run the game again. Next, we need to go check line. I guess I could cross off that triangle array. So next we need to check triangles with lines, and triangles and lines are going to look a lot like triangles and raycasts, and triangles and lines are going to look a lot like some of the other line test functions that we've written for the other shapes. In that this is going to look a lot like creating an array out of the line and just figuring out if the section of the array that is constrained within the line intersects the triangle. So rather than writing a bunch of code all over again, I'm going to say var direction is going to equal line dot finish dot sub line dot start, and we're gonna normalize this because we want this to have a unit length of 1. And we're going to create ourselves an array. Var array is going to be a new call array. And this is going to have an origin, which is going to be line.start. It's going to have a direction, which is going to be the direction that we just calculated a moment ago. We are going to create ourselves a little hit info. Var hit info is going to equal new raycast hit information. If self.check ray, taking the ray and the hit info. So if a collision is detected between the ray that the line lives on and the triangle, then we can simply return true if hit info.distance is less than or equal to line lowercase line dot length. So if the distance between the start of the line and the oh, that should be returned. If the distance between the start of the line and the location of the hit is less than the length of the line, then you know that there is a collision somewhere between the start and the end of the line with the triangle. Otherwise, there is none. And we can just return false at the end. This should be it for triangles and lines. If I were to go in here and zoom in and create myself a triangle, and if I were to, let's see, create myself a line. Okay, you know what took me like 15 minutes to figure out why my test wasn't working is because I was checking for the triangle against the line and not the other way around, and I need to go in call line. I need to turn that around and say return triangle.check line, taking ourself as a parameter. Also, while I'm on the subject, is it worth going into ray and turning that around too, saying return triangle.check ray, taking ourself and the hit info? Yeah, I think I'll do that. So you're going to notice that we are going to run into the same little issue that the triangle and the line had, and I've updated my test scene a little bit so that we can have a line that is generated with a random rotation in space rather than when it's aligned with an axis, because that is a little hard to see visually. So if I'm going to generate a triangle, and if I were to try to rotate the ray through it, you can see that, and I had it momentarily. We're only cutting through a little bit of the triangle at the bottom here, which is maybe not ideal. But anyway, you can see that we have the shape overlapping. We can see that if I move the line forward or backwards, we will start or stop overlapping. It is really hard to... Can I move this thing like up and down? Let me generate a better triangle like that doesn't suck. Hang on. Alright, that's a little bit better. So you can see that if I were to have the line piercing through the triangle, we have a collision detected. If I were to move it to the side, we would stop having a collision detected. If I were to move it... Can I move it in or out, or just, not really? Okay. I didn't make my test that fancy. If I were to rotate it, you would see what I mentioned earlier, in that we are only going to be detecting a collision with the triangle from the one direction. And again, if you want to account for both of these, it should not be too difficult to reverse the direction of the triangle and check for a collision between the line and the backside. Or you could do this some other ways. You could, in addition to checking for a ray that originates at the start of the line and goes in the direction of the end of the line, you could do it the other way around. If you were to change the check ray code so that the check ray method also will detect a collision with both sides of the triangle, check line will have that built in because check line is just a fancy wrapper around check ray anyway. But again, triangles are generally one-sided in computers. If you want to, it should not be too much work to, as I said before, reverse the direction of either the plane of the triangle that you're checking the raycast against, or reversing the order of the vertices in the triangle or something like that. But I don't want to spend a great deal of time doing that in this video, and I don't think it's something that you will generally be doing often anyway, so I'm going to leave it for now. So, let's see. I can commit some changes. Yeah, I've made my line test a little bit nicer, as you can see. Let's just commit this at once. If you want the code for this, look for the GitHub repository down in the video description. Branch week 13 triangles and lines should be what we did today. I should have a week 13 release by the time this video goes up as well. I have a Patreon, so if you want to contribute towards these videos being made, there will be links to that in all the usual places. You can see some fun things like your name in the credits at the end of these videos. You could hear a verbal shout out at the end, featuring yourself. You could see a bit of a preview of my future plans, which I attempt to stick to. These last few weeks have been a little bit off the rails. Anyway, if you wanted to pledge, I would definitely appreciate it. Otherwise, I try to post about 2 game dev videos a week, one of these and one Let's Make a Tower Defense game, which is hopefully going to be nice and wrapped up by the end of the year. Fingers crossed. I hope you all found this useful. Next time I will be taking on triangles versus triangles, one way or the other. And I will see you all later. Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games, and today it's time for the big one. Today we're going to figure out if 2 triangles intersect. So this is going to be a bit of an ordeal. There's a couple ways that you can test triangles for intersection. You may have actually seen one of them before. This on the screen right now is some very old, and by very old I mean it's from like 1997. It's not super old as far as the world as computers go. Anyway, this is an algorithm developed for triangle-triangle collisions by one Thomas Moeller. You may have seen it floating around the internet before. This is valid. It'll work if you want. You can convert this to GML. You'll need to use some tricks to convert very macro-heavy C code to GML, but you can do it if you want. I am not going to do this. I am going to instead use a combination of a couple different tricks to test for triangle intersections. Right off the bat, I'll say that it should be possible to just use the regular separated axis theorem to do 2 triangle intersections, but I unfortunately was not able to get that working. That's actually the main reason that I was a little bit late posting some of these collision videos, was because I was trying to figure that out. I actually wrote to the author of the book for advice on straightening that out, but unfortunately I did not hear a response in time for this video. So instead I'm going to rely on a few different tricks to figure out if 2 triangles are intersecting. So let's start in ColTriangle, and we're going to ColTriangle's check triangle method.
Hey.
So I said that we were going to be relying on a few different tricks to do this, and the first thing that I'm going to do to check to see if 2 triangles are overlapping is I'm going to get the planes of both triangles and see if all 3 points of one triangle or the other are on the same side of either of those planes. So let's get down to business. First, var plane A, I'm going to call this is going to equal self.getPlane. The second one, var plane B, is going to be triangle.getPlane. Next, we're going to use the plane equation that we wrote out a few videos ago to figure out a dot product-esque value that is going to give us some information on where each of the points of each of these triangles are relative to the planes. Let me call that P. Var PAA is going to be plane A dot plane equation, and the input point is going to be triangle.A. So this is going to be the plane of our self. I guess I could call this plane self if I wanted to make it a little bit more clear. But the plane of our self, plane equation against the other triangles A. Next, PAB and PAC are going to be plane equations for triangle.B and triangle.C. Next, after that, we're going to do this the other way around. So plane B, PBA is going to be plane B dot plane equation of our self dot A, B, and C. In this, just basically reversing the order of the triangles. And if all of the points of triangle A are on the same side of plane A, then there is no intersection between the triangles because the points are all on the same side of the plane. There is no crossover. If all three of the points of our own triangle are on the same side of plane B, same deal. You do need to test both of these because it is possible to have, for example, the points of triangle A on different sides of the plane of triangle B, but the reverse not being true. So you could go about doing this the long way. You could say if sine PAA equals sine PAB, and PAA is not equal to 0, and sine PAA equals sine PAC, then you could just return false, and then you could do this for vertices, and then you could do this for the other three vertices as well. You do need to check to see if the results of these plane equations are not equal to 0, because if all three of the points lie on the plane, that means the two triangles are coplanar, and you have to do something else to check if they intersect or not. However, this is a bit of a long and unwieldy line of code, so instead I'm going to first check if PAA multiplied by PAB is greater than 0, and PAA multiplied by PAC is greater than 0. And that is going to accomplish the same thing, but it's going to be a little bit less code. So when you multiply these together, if they have the same sign, then the result is going to be positive. If they have different signs, the result is going to be negative. And if they're both 0, then the result is going to be 0. So this accomplishes the same thing, but it's somewhat more efficient, and it's somewhat less code, and it's somewhat easier to read, I think. And then we can do this same thing again for PBA, PBB, PBA, and PBC. So again, we are going to check if the other set of 3 points are on the same side of the plane, of the other plane. And failing all this, we are going to return true. And there's going to be more that we're going to do between line 427 and 429 to work out some extra special cases where this may or may not be an intersection that we are not detecting here. But if I were to run the game now, then we are going to see that this should include a number of scenarios. You can see that we do indeed have a collision here, but it is correctly detected. If I were to move one triangle into a certain specific location, you can see that we are detecting false positives. These triangles are not actually intersecting, but the game currently thinks that they are because the 3 points of both triangles happen to be on different sides of the plane of the other triangle, even though there's no actual intersection. If I were to move one up or down, you can see that collision is no longer being detected side to side. And this is generally working in a lot of cases. I did write in a little bit of code to these demos to, let's see, to allow me to generate 2 triangles that are on the same plane. And in this case, right now, currently, any arrangement of these triangles, no matter where they are, will result in a false positive because the signs of these plane equations are all going to be 0. None of these returns are going to happen, and then we're just going to skip to the end. We're going to return true. This is actually the heart of the problem that I was having getting this working with the separated axis theorem, was that coplanar triangles were returning false positives under a lot of situations. I was unfortunately not able to get rid of all edge cases under those conditions, and we're just going to have to do this a different way. I was hoping that wasn't going to be a problem because the SIT is indeed a rather useful solution in a lot of cases, but was not meant to be, apparently. So I'm going to close the game. I'm going to open up GitHub Desktop. I think I'm going to... Let's commit some of these changes first. This was just a little update to the test. Ruling out collisions between triangles using the plane equation. If both of these triangles do happen to lie on the same plane, I'm going to, I'm just going to return true here for now, and I will come back to this later. Figuring out if both triangles lie on the same plane, you can do this the long way. You can say PAA equals 0 and PAB equals 0 and so on and so forth. You could also just compare the planes. You could see if the two planes of the two triangles are the same. You could say if plane A dot distance equals plane B dot distance, and the absolute value of plane A dot normal dot product against plane B dot normal. If this whole thing equals 1, because in this case, if the planes are one-sided, so you could have two planes that are visibly occupying the same space, but they will have opposite normals, and you can compare the normals to each other using the dot product. And if that dot product is 1 or -1, and if you take the absolute value of that, if the absolute value of that dot product is +1, that means that the planes are in roughly the same place. We're just going to return true, and we will deal with this later. Next, we're going to use the separated axis theorem, the good old separated axis theorem for a little bit. We are going to, let's see, let me define var. And in a couple places in this code elsewhere, I think I've called these values something like, yeah, down here. Diff AB is going to be self.b.sub self.a and that sort of notation. But let's go with BC and CA, and this can be C sub B and A sub C, like this. I would call these variables diff AB, diff BC, and so on, except I'm going to need these for both triangles, and I want to make the names a little bit less confusing. So let's call it self AB, self BC, self CA. And for the other triangle, for the incoming triangle, it can be other AB, other BC, other CA. Triangle.b.sub, triangle.a, and so on and so forth. And these are essentially representing the edges of each triangle. I really should comment this code, shouldn't I? I'll comment this code before I push it to GitHub. Next, we're going to do a little separating axis test, and I'm going to say var axes is going to equal an array, and we are going to be dealing with, I believe, more axes than we were with some of the other ones. For example, ab triangle. Oh no, ab triangle also used a lot of axes. All right, that's fine. Anyway, we're going to be using 11 axes here. First is going to be self.normal. I suppose it might be a good idea to dot normalize this. You can also say, actually, is when our normals are calculated. This is not a variable, is it? Yeah, this is a method call for get normal. Okay, that helps a little bit. The first axis is going to be our own normal. The second axis is going to be triangle.get normal. So that is the normal of the other triangle. And the other 9 axes are going to be, for example, other AB dot cross self AB, and then other BC dot cross self AB, and then other CA dot cross self AB, and then you can see where this is going. We're going to cross each of the edges of one triangle against each of the edges of the other triangle. So this can be, I'm going to separate this into like sections. Other AB cross self AB, other BC cross self AB, other CA cross self AB, other AB cross self BC, other BC cross self BC, other CA cross self BC, and then the last one is going to be the same 3 edges cross against self CA. For a quick sanity check, on the left we're going to have other AB, other BC, other CA, other AB, BC, CA, AB, BB, BC, CA, and on the right we are going to have AB, 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 BC, 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 CA, CA, CA. Just for a quick sanity check to make sure that you didn't duplicate any of those axes or otherwise mistype them. And from here we can just run the regular good old-fashioned separated axis theorem. So we're going to say var for var I equals 0, I is less than 11, I plus plus. If not, call overlap axis, and shape 1 is going to be self, shape 2 is going to be triangle, and the axis is going to be axes index I. So if there is an axis of separation between ourself, the other triangle, on any one of these axes, we are going to return false. Otherwise, return true. And again, we are currently not accounting for the special case where the two triangles are coplanar. We're going to deal with that soon. So now, if I were to run the game, and if I were to attempt to generate one of those little edge cases where the three triangles, three vertices rather, of each triangle are on different sides, that's actually an intersection there, isn't it? Different sides of each other. Okay, here we go. So if we have a case where all three of the vertices of one triangle are on opposite sides of the plane of the other, if I can get them all in view at once, that'll be helpful. We no longer have a false positive being reported here. However, if I were to move them into each other, we now do have an intersection being detected. However, if I were to again go back to the special case where these triangles are coplanar, we still do have false positives. That is going to be the subject of what we're going to deal with next. All right. You know what? I'm going to comment this before I commit. Okay, I've written some comments. Phase 1 is going to be testing if each of the points of each triangle are on the same side of the plane of the other. Phase 2 is what we're going to do next. This is when triangles are coplanar. Phase 3 is the regular old separated axis theorem. And now it's time to do some math. So, in turn, there's going to be a couple different tests that we're going to do to see if two coplanar triangles are colliding with each other. One of them is going to be simply checking to see if a set of points, if each of the points of one triangle are inside another. We already know that the points are on the same plane. There's a few different ways that we can do this. We can use the barycentric coordinates from not too long ago. I think for the sake of simplicity, and this is not going to be completely optimal code, none of this is really, but for the sake of simplicity, I can say if new call point containing self.a.check triangle, the incoming triangle. So if if point A on our own triangle is within the incoming triangle, then we can return true. We can do this for the other 5 points in this equation. So if call point self.a, self.b, self.c, check triangle against the incoming triangle, we can do this the other way around. So if the points of the incoming triangle are inside of our self, then we can also return true. And if none of those happens, we can return false. This is not the end of the story. The end of the story, this is going to account for most cases of triangle-triangle collision, but unfortunately, the last one is going to be a little bit more work. Let me zoom in. Let me create two triangles that are coplanar. We have shapes overlapping here, but if I move the one away, we no longer have an intersection. So let's see. There are still edge cases. Let me see if I can work out another edge case. It is possible, and you can visualize this in your mind. It is possible to have two triangles intersecting that do not have any 2 points within each other. And if I were to attempt to generate a triangle that does that, here we have one. You can see these two triangles are coplanar. They should be detecting an intersection, but they are not. If I were to move one so that we have one of the corners inside the other, here we have an intersection. If I were to move it away, we do not. We are detecting a false negative here. And this is the final special case for detecting triangle collisions that I need to test. So the core of the problem that we need to solve from here on out is figuring out if two line segments intersect each other, because if none of the points of one triangle if two triangles are coplanar and none of the points of either triangle are within the other, then you know that two of the edges have to intersect somewhere. And there's a part of me that wishes that I'd implemented down in the collision line class if I'd implemented collisions between lines and other lines, but I have not. And honestly, this is an easier problem to solve in 2 dimensions anyway, or at least I think it is. So that's what we're going to do. First, we need to project each of the triangles onto a 2D plane so that we can turn these into 2D triangles. This is not going to just be like the XY plane or the XZ plane or the YZ plane or anything like that, because these triangles could be oriented any which way. So instead, I'm going to go into the collision stuff, into the collision helper code file. And is this where, okay, yeah, this is collision helper. This is where I'm looking for. I'm going to define a few more helper functions. One is going to be function, let's call it call project onto plane. This is going to take 4 arguments. The first argument is going to be a vertex. The second argument is going to be an origin. The third argument is going to be, I'm sorry, this is going to take 5 arguments. Normal, E1 and E2. I am just going to read through this code as quickly as possible because I want to get through it. I'm going to first define var. Let's call it S is going to be norm dot vertex dot subtract. And that's just sub, not actually spelling out subtract origin. This is not going to be a long function, but I'm just going to go through it quickly so that we can so that I don't have to spend a great deal of time. On it. First, I'm going to define var t1 is going to be, let's say e1 edge1 dot against vertex dot sub the origin. The next line is going to be var t2 is going to be e2 dot, and it's going to be the same thing, subtracting the vertex from the origin. If you want to save a couple computer operations, you can do this once, save it to a variable. That's just a general rule for a lot of the codes that I've written in this 3D collision series. And then finally, return new vector3, composed of t1, t2, and 0. This could be a vector2, but I do not have a class for a 2-dimensional vector anywhere in this project, so I'm just going to be going with a vector3 with a z-coordinate of 0, because we are going to be, by and large, disregarding that. Okay, so we're going to come back to that. This is call shapes. This is where I want to be. So before I make use of the function that I just defined regarding projecting a vertex onto a plane, let us first define a few more values. First, var origin is going to be, I'm just going to arbitrarily make this self.a. Not arbitrarily, but it can be any of the points on the on our own triangle here. And the rest of this is just going to be defined in relation to the origin self.a. Next, var norm equals self.get normal. You may note that self.get normal has been calculated a couple of times. Actually, has it? Oh, it's calculated farther down. You may wish to define some common terms, such as getting the normal of this triangle, and just like stick them at the top of this method call. If you want, same thing for the edges down here, like self AB, self BC, self CA. I'm not going to do that. I don't want to write minimalist code. I want to write legible code. And in any case, this up here, inside the 2 coplanar triangle checks, and this down here in the SAT check is never going to run in the same method call anyway, because they're in separate branches. Regardless, next, let's say var e1 is going to be self.b.sub self.a. Again, that is the same value that's down here. If you wanted to, you could call this like self e1, self e2, self 3 e3, other e1, other e2, other e3. Anyway, and lastly, var e2 is going to be e1.cross against the normal. Next, we're going to start projecting each of the vertices of each triangle onto the plane, and we're going to create 2 new triangles that are composed of those projected points. Let me call it var. I'll call it self projected is going to equal a new call triangle, and we are instantiating a new triangle in here but it's not going to really be used for a lot. It's just going to be a container for points, really. We're not going to be calling any methods on it. And I'm going to break this over multiple lines because if I were to do it in one line, it would be rather long. The first vertex, vertex A, is going to be call project onto plane. The vertex is going to be self.a. The origin is going to be the origin from here. The normal is going to be the normal from up here. E1 and E2. And the second and third vertices are going to look very much the same. So we're going to project all three of the vertices of our own triangle onto the plane defined by the origin, which is essentially the distance from the world origin, and the normal of the triangle. And next we're going to our other projected is going to be new call triangle, and it is going to also look rather the same, except instead of projecting our own points onto that plane, we're going to project the points of the incoming triangle onto that plane. So now we have two triangles. They're going to both lie on the XY plane. All three of the z coordinates of both triangles are going to be 0, because remember, call project onto plane just returns a new vector 3 with the projected vertices and 0 on the z-axis. Projecting vectors onto an axis, by the way, or rather projecting 3D vectors onto a plane, this is code that you might want to reuse for other purposes. Projecting vectors onto a plane is something that you might want to do elsewhere in 3D games, but I don't want to make a huge deal out of it. Just if you're ever doing anything and you see code that looks like this, now you know where it comes from. Anyway, we now have two triangles that are projected onto a 2D plane. And what we have now is simply a problem of figuring out if any pairs of 2D lines intersect. So the way that we're going to do this is I'm going to go back to the helper functions code file. I'm going to define two more functions. One is going to be function call lines intersect. And instead of taking like a line object or anything, I'm just going to take 4 points A, B, C, and D. This might start to look a little bit familiar from geometry class. I'm going to define a third function, which is going to be function call points are counterclockwise. This is going to take 3 arguments, 3 vector 3s, A, B, and C. Really 3 2D vectors, because again, the z coordinate on each of them is going to be 0. And this might be a little bit counterintuitive. When I came across this code initially, I had to think through it a little bit. We're going to be figuring out if two 2D lines intersect by checking to see if if all 3 of the points are defined in counterclockwise order. If you remember systems of equations for Algebra 1 in school, you might be thinking of ways to check to see if 2 line segments intersect by solving a linear system of equations and like testing the value to see if the point of intersection is within the range of the actual line segment. But that's going to be even more code than we've already written for this video, and I don't think anybody, including me, wants to sit here for any longer than necessary. So we're just going to write a little bit to figure out if any 3 sets of points are in counterclockwise order from each other. To do that, I'm just going to return c.y minus a.y. The quantity of that multiplied by b.x minus a.x, the quantity of that. And we're going to test if this expression, we're going to return a Boolean, is this expression less than the quantity of b.y minus a.y multiplied by c.x minus a.x. Close parentheses, that is all for call points are counterclockwise. And in the intersection function, to make a long story short, if you have 2 line segments, let's call them A, B, and C, D. To use every geometry teacher's favorite set of words ever, they're going to intersect if and only if essentially you find an axis of separation between them, as we've been doing for a number of the prior videos with the separated axis theorem. So, and this is going to be a little bit long to type out because of the long function name that I decided to give this one. But our return statement for this function can be a single expression. We're going to return Points are counterclockwise. A, what did I say? A, C, and D is not equal to points are counterclockwise. B, C, and D. That is going to be one expression. And let me dump this on a second line. Points are counterclockwise. A, B, and C is not equal to points are counterclockwise. A, B, and D. And that should be our entire expression. All right, parentheses are in the right place. Good. This is a function which we'll check to see if two-dimensional lines intersect. And now we can hop back over to the check triangles code, and we can actually use this. So both triangles have 3 lines. We have 3 times 3 equals 9 intersections to test. For example, I can say if call call lines intersect self projected dot A self projected dot B is going to be the point of one line segment, and the second line segment is going to be other projected dot A and other projected dot B. If these 2 line segments intersect, return true. There is a collision between these 2 triangles. And now let us do this again for all of the other 8 pairs of line segment intersections. This is going to be a bit like the 3 axes of separation down here, and that we're crossing one into the other, but it's not going to be quite as short as the other code was. I keep typing D instead of A. So again, if you want to do a sanity check, AB, 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 BC, 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 CA, CA, CA on the first line segment, and AB, BC, CA, AB, BC, CA, AB, BC, CA on the second line segment.
Hey.
And if none of these 9 functions return true, then we can prove that these 2 triangles do not intersect. So I'm going to run this hopefully for the last time. I am going to generate 2 sets of triangles that are lying on the same plane, and let's see if I can generate one of those like edge cases here. I can. Okay, barely. You can see these triangles are on the same plane and they are intersecting without any of the points being contained within the other. And collisions are correctly being detected here. If I were to move outside of the plane, we can see that we no longer have collisions being detected against each other. That is great. And if I were to generate any other 2 triangles, we should be able to see that any and all edge cases will be accounted for. If I have one that's coplanar with the XY plane and another that's not, we have collision correctly being detected. Okay, and so on and so forth. So this is a lot of code, and as you probably summarized from this video, this is not very efficient. Checking to see if 2 triangles intersect each other is actually something that you really do not want to do very often, because it is expensive. If you're thinking back to the Thomas Moeller version of triangle-triangle intersection, that is slightly more efficient, although it's still a lot of math, so it'll still be fairly slow. You can actually work out elements of the code that are similar between these 2 methods. For example, checking the plane equations to see if all 3 of the points lie on one side versus the other. He does a slightly different, well, really a very different way of checking to see if the like the intervals of the 2 triangles overlap on any axis. But that is slightly more efficient code. It's just like if I were to try to read that, and if I were to try to do that on the video, it would be about as much fun as me reading from a phone book. And the point of these videos is for me to explain how it works as best as I can, so I kind of opted not to do that. I was originally hesitant as to whether or not I wanted to include triangle versus triangle intersections in this series to begin with, because it is so slow, and generally if you have 2 3D meshes, you're going to be dealing with hundreds, if not thousands, of triangles that you're checking against each other. And there are ways that you can optimize that, but It's still generally a very slow process and not something you really want to do if you can get away with it. When we get to checking 3D meshes for collision, you're going to see how unpleasant triangle collision detection becomes very quickly. And also, actually, I can run this in debug mode, and I can run this through the profiler. Yes, please. If I were to open up the profiler, where is the others? That's buffers. Debugger, Windows, profile. Oh, it's over here. And if I were to look at how long, for example, the point and check points take, and we can move these around. And if I were to stop profiling, it is this function call here. A single function call for checkpoint is costing, that's 2 microseconds, which is pretty fast. If I were to instead check, for example, maybe a sphere versus an ab. Let's see, so that's an ab and an ab. I was thinking a sphere and an ab, like this. And if I were to run the profile on this instead, and I'm gonna let that go for a couple of seconds, this is taking 15 microseconds instead of, which is a little bit more time than point and point, but ab and sphere, it's still pretty fast. 15 microseconds. You can get away with doing this hundreds of times per frame, and you'll be fine as far as performance goes. However, if I were to change this to what is triangle? Triangle and triangle. We can run the profiler on this, and this is going to be a lot more costly than any of those other 3D collision tests. I'm gonna let this run for a couple more seconds, and you can see that this is taking up almost a quarter of a millisecond, 250 microseconds plus every time for a single function call. It is a lot more math. A lot more lines of code are running in triangle than in, for example, sphere ab, which is really just checking to see the distance between 2 points is less than or equal to the radius. And this is something that will not scale nearly as well as collisions between primitive shapes. Collisions between primitive shapes are very nice performance-wise. When it comes to 3D collision checking, collisions between triangles are not.
Hey.
Let me test ab versus ab. That's not an ab. Ab versus ab. Whether or not they actually intersect is a little bit secondary as far as performance is concerned, because I'm more interested in like the average case. But I guess if I really wanted to test the average case, that would be like moving these shapes around in different ways. Ab takes about as much time as ab sphere did. Regardless, triangle collision is here, and you can choose to use this if you want. I am going to commit this last code to GitHub. And again, there are more efficient ways to do triangle intersection, but any way you do it is still going to be a lot more costly than the other collision detection algorithms, just because it's going to be a lot more math happening. Maybe instead of being like 16 times slower than ab, some versions, maybe Thomas Muller's version of triangle might be just like 8 times slower. Either way, it's still less than ideal. So let me close the debugger. Next time I want to do something easy, I'm going to start assembling triangles into 3D models, and I'm not going to be getting into optimizing 3D models using things like Octree hierarchies and that sort of thing. But I will be setting up some 3D models that we can test triangle collisions with in bulk. I'm going to be importing some 3D models into the game, or into the test program. I keep calling it a game, and we're going to be creating a model data structure. Until then, I hope you all found this useful. If you want the code for this, look for the GitHub repository down in the video description. I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Tower Defense game, which is almost done. There's like 3 videos left in that series. I have a Patreon, so if you want to contribute towards any of these videos being made, look for the links to that in all the usual places. You could see some fun things like your name in the credits, or a shout out at the end, verbally, on the end screen. So if you wanted to pledge, I would definitely appreciate it. Otherwise, I hope you all found this useful, and I will see you all later. Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. Today we're going to do something easy. In the last couple of weeks we have dealt with 3D collisions between triangles and other shapes, and that has been quite a bit of math. Today we're going to do something easy. Today we're also going to do something that is not very good and you don't want to actually do in practice in the real world anywhere ever, and that is going to be checking for collisions with 3D triangle meshes by iterating over every single triangle in the 3D collision mesh and checking it for collision independently. Anyway, here's a palm tree. This is one of the Kenny 3D models from Kenny.nl's one of his low poly asset collections. And today we're going to be using it as our test dummy. We are going to be using this to detect some 3D collisions against. As you can see, none of the other shapes that I can add to the scene do any sort of collision checking with this thing. Let's see. That is a single triangle. That is a plane. That is a line. That is an axis-aligned bounding box that we can move around. And how do I don't know what the controls for this thing are. No 3D collisions are detected is the point. If you want to take a quick look through the code that's driving this test project that I've written on my own time, one, we can see that we are loading another vertex buffer from a file. Instead of being called like grid or ab or plane or whatever, this is just a tree.vbuff. And we are instantiating one of those if you hit the M key or the 6 key on the number pad on the keyboard, just like we are with the other collision test shapes. Let's see. The way that this works is a little bit different from some of the other collision test shapes. So the call test mesh takes a vertex buffer as its input, as do the other shapes, but it also will do a little bit of converting that to a regular buffer and extracting all the triangle information and feeding the triangle information into an array of call triangles. I'm not going to get into how you would turn a vertex buffer into a regular buffer and do things to it. I've done that in several videos in the past. I will have links to that around. And then once that is done, the triangle array is fed into a new constructor for a collision mesh, which is a new struct type that I have created. So the collision mesh takes an array of triangles. Triangles are in turn another collision type in the, where are they? Up here. This one, this big thing here that I'm scrolling through, the call triangle. And that's it. It doesn't contain any transform information, at least not yet. I'm sure I'll be getting to that soon enough. It's got some dummy methods, check point, check sphere, check ab, check plane, check triangle, check mesh, check ray, check line. At the current moment, these all return false. I've also added to all of the other collision shapes. I'm not going to scroll all the way back up there. I've also added to all the other collision shapes check mesh method, which just turns the equation around and calls the meshes check whatever method. This should be check ray. Did not turn that around properly. And did I make the same typo on line? I did not. Okay. So we're going to do this in a very simple way, and I want you to pay attention to some certain things when I do this. One, I want you to take a wild guess as to what the frame rate is going to be before I run the game, after doing all this. And two, I want you to actually look at the frame rate that we're getting when we run the game and compare that to what you expected. For reference, these trees that I'm working with here are, I want to say, about 400 triangles. All right, this is the 3D model. This is 488 triangles, which is not small, but it's also definitely not huge. So to do this the easy way, we can write a little for loop in each of these checkpoint, check sphere, whatever methods. We can say for var I equals 0, n equals array length self dot triangles I is less than n. I++, and we can say if self.triangles index I.check point, the input point, if there is a collision, return true. If there is not a collision at the end of the day, return false. And we can do this very, very similar strategy for each of the rest of the these shapes. So check sphere, check ab, ab, AABB, check plane. What happened here? Copying and pasting the wrong things. check triangle. So checking each triangle against another triangle. Check mesh. We can check each triangle against the mesh independently. This one's a little bit elaborate because this is going to jump through several stack frames. Check one mesh is check mesh is going to loop through its triangle. Each of its triangles, it is going to have that triangle check the mesh. When triangles check mesh, that is going to get turned around and call meshes check triangle. And that is for every triangle in the same mesh we are going to check. And they need to update these variable names. I'll get there in a minute. We need to check triangle against a triangle. So that's like 4 stack frames that we have to jump through. And if you think that mesh collision checking by doing this linear search like this is not going to be super efficient, well, you'll see. Let's see. The last thing I need to do is update all these variable names. And raise also take the hit info. Plane, ab, and sphere, like that. Okay, so this is nominally all we're going to do in this video. This was a lot of what one might call busy work, and we're just iterating over every triangle in a mesh and checking that triangle, checking each triangle for a collision with whatever the incoming shape is. And let's see, the other thing, I did write some code so that you can move the triangles around with the arrow keys the same way that you can with the other basic shapes, but that's a little bit more involved since considering that collision mesh shapes do not contain transform information yet, which you can totally do. You can totally store a transform matrix and then matrix multiply each triangle or whatever by the transform matrix before checking it, but we're not going to do that today. We just go in a loop and update the positions of each of these triangles manually. So let's run the game, and as I said when I started typing today, just take a wild guess as to what the frame rate is going to end up looking like when I start checking meshes against other shapes, and compare that to what we actually see. So if I create a collision mesh and check it against a single point, this is a single point in shape, I can move the point around, and you'll see that we're getting about high 30s frames per second just by checking this one single point against a triangle mesh containing almost 500 triangles. We are not checking points against triangles is honestly not super useful because triangle meshes do not inherently have a concept of inside versus outside. So whereas, for example, a sphere and a point has concept of whether or not the point is inside the sphere or not, collision meshes kind of don't by default. And this will only return true if the point lies flat against one of the triangles of the mesh. Next, we can test this against a collision sphere, and this is where things start to get interesting. I can zoom in a little bit. If I were to move the mesh, okay, maybe I should look at it from above. If I were to look to move the sphere in or out, we can see collision is being detected correctly. We can see that there is space here. There is no collision being detected with the sphere, but the frame rate is diving sub 20. Which is just utterly beautiful. If I were to move the sphere up, we can see that at the point where the top of the tree starts to pass through the sphere, we do have the shapes being detected as overlapping. If I move it up further, we can see that the collision goes away. If I mouse over what is it? Oh god. The tree mesh, you can see that we do indeed have correct raycasting. I have a raycast hit being detected. Well, correct. It is functional raycast hit being detected anyway. Against each of these triangles, you can see that if I were to point my mouse at the trunk of the tree, we have the ray indicating its hit position and also the normal of its hit position. However, there are certain places where the wrong triangle will be detected, and by wrong triangle, I don't mean that we will be erroneously detecting a raycast into the triangle. I mean that there may be a triangle that is closer to the origin of the ray, in other words, the camera, that should be detecting a ray hit, and instead it seems to be detecting one with one farther away, and that is because we are doing a linear search throughout the triangle mesh, and whatever the first triangle that the ray happens to hit happens to be, that is the one that it will return. And it will it will not wait to see if it can find a closer by raycast hit. You may also notice that while for the most part, and I'm going to zoom back out a little bit, while for the most part the frame rate is sub 20 for the sphere versus tree, sphere versus mesh, there are certain places that you can put the sphere which will cause it to increase somewhat. So if I were to, oh come on, moving this thing around is hard. I'm just going to give you some insider information. In the internal order that the vertices are stored in the triangle mesh, in the vertex buffer, the leaves on the top, the triangles on the top happen to be earlier in the vertex buffer than the triangles on the stem. So if you detect a collision with any of the triangles up on the top over here, you're going to exit out of the loop earlier than if you were to check for a collision with one of the triangles on the bottom. You can see when I move the sphere down, the frame rate plummets back to sub 20s. This is not information that you should ever have to depend on, because if you're going to do a 3D collision check against a collision mesh, you should be doing something a little bit smarter than what I'm doing now. Anyway, moving on to some of the other shapes, we have abs. I can move the ab up. This is actually even worse than the sphere was, because axis-aligned bounding box collision checks are a little bit more involved than sphere collision checks. We have, it looks like we're dancing between 11 and 12 frames per second, occasionally dipping down to 10. Again, if I were to check the axis-aligned bounding box against the top of the tree, that is going to be slightly more performant than checking it against, for example, the bottom of the tree. What other shapes do we have? This is an individual triangle. Same deal. It looks like we actually have the triangle performing slightly better than the axis-aligned bounding box, which actually surprises me. I was expecting the triangle to perform worse. You can try the other shapes. There is a plane. We can move the plane up and down. We have the plane overlapping or not overlapping. And possibly the most fun one that we can do, we have two meshes, and we're checking for intersection between each of these meshes. And I hope this is going to like record without crashing my computer, because we are getting sub 1 frame per second here. Wow, that's impressive. So this is a bit of a lighthearted, fun video. I'm going to just close the game now so that I don't have to like have this chugging away on my computer. Don't do this. Next time, like I said, we will be talking about ways to organize collision meshes into a hierarchy so that you don't have to check every single triangle in it if you're checking for collision. Generally speaking, you actually want to avoid doing mesh collision checks entirely. If you can approximate the shape of, for example, a tree with something like a capsule or something like an axis-aligned bounding box, you should. If you can approximate the shape of, like, for example, a building with something like an axis-aligned bounding box, you definitely should. I have not covered capsules or oblique bounding boxes yet, but those tend to be very useful when it comes to approximating collision shapes with things like walls or rotated objects or characters or that sort of thing. And also, and I think this is something that a lot of people have realized at one point or another, but if you do want to do a collision check against a mesh, you generally want to, instead of using the entire visible mesh with every single triangle, you generally want to use a simplified collision mesh for a mesh collision, because generally speaking, you can approximate the shape of objects. And if you do have an irregularly shaped object that you want to do a precise collision check against, you generally don't need the full however many thousands of vertices it might be. You generally only need maybe a couple dozen, maybe a couple hundred at most. Anyway, just for a little bit more fun, you may be wondering, this code has been running on the GameMaker virtual machine, which is the default way of running GameMaker games. You may be wondering how this performs if you run this in the Yo-Yo compiler, and the answer to that is better, but it's still not anywhere near what you would want in something resembling a game. So I'm going to just build this code using the Yo-Yo compiler, and we can see how this is going to perform. Compilation is going to take 1,000, I believe, lines of code in here, and that's gonna take a bit to compile. Okay, it looks like we're starting up, and okay, here we have a point against the point. That is about as inexpensive as it gets. We're just checking two vectors in space to see if they equal each other. We're getting about 4,000 FPS real here. If I were to give myself a collision mesh, we are getting about, it looks like 70 or 80. If I were to bring in a more complex shape than a single point, like an axis-aligned bounding box, we're getting now mid-20s, which is about twice the frame rate that we were getting before, although it's still not anything to write home about. Definitely don't think anybody wants to ship a game that's running at like 24 frames per second when all that's happening in it is like drawing two objects plus doing a collision check between them. And let's God forbid, let's do a mesh against a mesh. Okay, wow. All of 16 frames per second. Again, depending on where I attempt to check for collisions here, we are going to be seeing the frame rate. Okay, this is more like it. We're getting 1.5, maybe a little bit better than that, FPS real. Beautiful. Don't ever run this in an actual game. I don't know how many times it would be beneficial for me to say this before it starts to just get annoying. We'll be doing something better next time. I do hope that you found this little video fun. However, I am going to commit this code to GitHub all the same. I might not merge this one into master. I might just leave this on the week 15 meshes branch, just for a little bit of fun. Anyway, by the way, in case you're wondering exactly how many operations we're doing, or at least how many triangle operations we're doing, at most. And I do want to make a video on runtime analysis eventually, but if there are 488 triangles in the tree mesh, and each of those is checking against each other triangle in the tree mesh to see if there's a collision, we are doing at most 250,000 triangle checks per frame. You can see why that is causing the frame rate to dive. Triangle checks not being super efficient as it is. Anyway, what does my usual sign-off even consist of? I don't know. I try to post about 2 game dev videos every week. One tutorial, if you can count this as that, and one Let's Make a Tower Defense game, although I won't really be able to say that anymore after next week because that is officially finished. If you want the code for this, warts and all, look for the GitHub repository down in the video description. I have a Patreon, so if you want to contribute towards these videos being made, look for links to that in all the usual places as well. You can see some fun things like your name in the credits, or hear a verbal shout out of yourself at the end of every video. Maybe see a preview of my future plans once in a while. Otherwise, I can't really say I hope you found this useful, because I honestly hope that nobody ever uses code like this in an actual game. But whatever it is, I will see you all later. Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games, and it is time to start doing 3D collisions again. So the last time I left off with this project, we had 3D collisions between various shapes and between triangle meshes. They did not perform very well. I'm going to take a wild guess that most of you want your games to run faster than 17 FPS with a single collision detection between a tree and a block. So in the next couple of videos, we are going to do a little bit of work on the various data structures that represent these collision shapes, and we're going to make this run a little better. As always, standard disclaimer applies. This is part of a long-running series on 3D collisions in GameMaker that I've been working on for the better part of a year now. I highly recommend watching that series from the beginning before taking on this video if you have not already. So this video is not going to include a few things, but I do want to get to at least most of them in the future. One, as I mentioned, we're not actually going to be checking for collisions against 3D meshes today. Today we're just going to be setting up the data structure. Also, and I have a few friends who would be very upset with me if I didn't at least mention this, there are other ways that you can structure this data to accelerate 3D collisions, but today we're just going to be covering Octrees. Also, I'm not going to be dealing with things like translation in space or rotation in space with these triangle meshes, at least not yet. Strictly speaking, that's been the case for all of the 3D collision shapes that I've done so far, but since these triangle meshes are loaded from a file in this case, they're not even created at a certain point in the room. It's especially... At least I suspect it'll be an especially glaring omission in this video. Definitely we'll get to that eventually. I would consider that to be a pretty important thing to cover. So firstly, I'm going to go and delete all of this code, all of this for loop code, because I don't want to run it by accident and suddenly have the game giving me like single-digit frame rates. Mesh and ray and line. Okay, and I'll make the font size bigger. So I'm not going to be getting back to any collision detection code in this video. What I am going to do in this video is I'm going to set up the data structure, which is going to enable us to cut down on the amount of work that we have to do. There's a few different strategies for doing this that people have employed over the years, but the one that we are going to talk about today is the Octree. So as I'm sure most of you already know, the Octree is the lesser-known cousin of one of the earlier grunt-type enemies from The Legend of Zelda, and by using them we can... Okay, fine. Octrees are a kind of spatial partition, which subdivide a 3D triangle mesh into pieces. For a visual representation, I'm showing on screen right now a similar data structure known as a quad tree. These types of data structures subdivide triangle meshes into essentially halves, and they sort the triangles in the triangle mesh into one or more of the subdivisions. And this allows you, when you're doing collision checks, to only check for collisions with triangles that are in a particular region. Quad trees subdivide a mesh into four, quadrants: upper left, upper right, lower right. And if you did the same thing in 3 dimensions, an octree, as the name implies, separates the space into 8 sections. I don't know if there is a 3D equivalent of the word quadrant. Octant just sounds wrong.
Hey.
And you can do this recursively. You can subdivide each quadrant of a quad tree into its own quad tree, or in 3 dimensions, as you're going to see in this video, you can subdivide one section of an octree into its own inner octree. I was considering making general computer science videos on recursion and on runtime analysis before I did this one, but then I decided that I put this off for long enough. I don't want to put it off even longer. Maybe another time. So that is what we're going to be doing here today. We are going to be creating an octree based on an array of triangles. So the first thing we're going to need to do to set this up is we are going to need to be able to get the bounding box of a triangle mesh, of a triangle array. That's going to involve figuring out the minimum and maximum points of every triangle in the triangle array. And we can do that. We can initialize a few variables. I'm going to say var bounds min is going to be a new vector 3. I'm going to initialize this to a few values. Let's say infinity, and infinity. It may sound weird to initialize the minimum bounds of an object to infinity, but when we compare each further point in the triangle array to the minimum bounds, anything is going to be less than infinity. So that makes infinity a good default value. Likewise, var bounds max is going to be a new vector 3. This is going to be negative infinity, and negative infinity on all three axes. So to get the minimum and maximum of the bounds of a triangle array, triangle mesh, I'm going to be using those two words interchangeably. I hope nobody minds. We can simply loop over the triangle array. So for var I equals 0, I is less than array length. This is probably a good time to remind everybody that I will not be writing 100% optimal code here. This for I equals 0, I is less than array length could be written in a slightly more performant manner, but I'm going to be writing what I hope is readable code here. There are definitely things that you can do, GML optimizations that you can use to speed things up, but those are not going to be included today. It might be another future video topic, come to think of it. So for every triangle in the array, I can say tri is going to equal triangle array index 0. And to update and to check the bounds of the triangle, we can simply say bounds min.x is going to be the minimum of what's already there. Bounds min.x try dot the first vertex dot x try dot the second vertex dot x try the third vertex dot x. And we can do the same for y and z. This is going to be very copy and pasty for the first couple minutes. Bounds min.y is going to be the minimum of the existing y and y of all three of the points on the triangle. And bounds max .xyz is going to be the maximum of bounds max .x triangle vertex a.x triangle vertex b.x and so on. So this is going to be very plug and play, as I said. I'm going to assign a new value, and this is going to be the collision mesh's self.bounds is going to be making use of one of the helper functions that I wrote a very, very long time ago now. A new collision axis align bounding box from min max. We already have the min, and we already have the max. This is going to create an axis align bounding box from these minimum and maximum values, as opposed to creating one from a position and a half extent, the way that the actual call add constructor would. So before I do anything else, I'm going to just insert a little bit of code And I don't want any of you to particularly worry about this. This is just going to be a little visualization that I'm going to add to the draw event of the call test mesh object. If you want to make use of this debug draw method for anything yourself, you're more than welcome to. It literally constructs a wireframe based on the edges of a cube, and it draws them with a line list. It draws them as a line list. It's just not particularly relevant to the video at hand, and I don't want anyone to look at that and spend a great deal of time getting hung up on it because they don't know what it's doing.
Hey.
So getting back to a collision mesh. The bounding box is just there to help us out. The actual collision structure for the Octree. I'm going to go and create myself a new script. I'm going to call this call _ Octree. Really? GameMaker. Alright, there's a weird, at least in the version that I'm using, I don't know if they fixed it in future releases, but there's a weird issue where GameMaker will, like, randomly open the folder that a resource lives in if you hit a certain hotkey. It's very strange. Anyway, let's see, I'm gonna call this call Octree node. Actually, no, I'll just call it call Octree. This is going to be a constructor. The constructor for this Octree is going to take two parameters. One is going to be the bounds, and one is going to be the mesh. The bounds are the bounding box that defines the bounds of the Octree, and the mesh is just a reference to the object that the Octree is part of. So in our case, this ColMesh. So let's just assign these to local variables, to instance variables rather. Self.bounds equals bounds. Self.mesh equals mesh. Two other things I'm going to define. One is going to be self.triangles. This is going to be an empty array for now. We will populate that later. And self.children, CHILD is going to be initialized to undefined for now. So this is the constructor for an Octree. It will not do anything very interesting for now, but now that we have the constructor added, I will go back to the collision mesh and say self.accelerator is going to be a new call Octree. The bounds are going to be self.bounds. This is the bounding box of the mesh as a whole, and the mesh that we are going to pass is going to be obviously just ourselves. Next, let's assign something to the triangles array inside the Octree that we just instantiated. There's a part of me that thinks that this should be done in the constructor via something like in the Octree constructor self.triangles equals mesh.triangles, but this is likely going to just not really help us out at all with some of the things that we want to do with the Octree in the future. So instead, self.accelerator is going triangles is going to be equal to triangle array. So this is just going to contain a reference to the very same triangle array that was passed into the mesh constructor. If you're following Gabor Zaur's game physics cookbook, which, as I've cited on numerous occasions, is where I am getting a lot of this information from. He's doing a little bit more when it comes to Octrees in terms of like C++ pointer spam, but since we are using GML, we have the luxury of not dealing with C++ pointer spam, which I think most people can agree will generally make our lives easier all around. So if I were to run the game now, nothing would happen. We haven't really done much. If I were to instantiate a triangle mesh, nothing is going to happen. You will notice, by the way, one of the off-screen changes that I made is that when you construct a test mesh, the process is timed, and it pops out in the console how long that process took. I want you to pay attention to that, because while right now it is pretty quick to instantiate a triangle mesh, once we start to optimize this a little bit, it is going to take quite a bit longer. So first, before I do anything else, let me make another commit. Let me say this is going to be create an Octree. If I were to go back over here, and I think I'm going to split this into two panes right now so that I can... No! Workspaces, help. What are you doing? So that I can see both the collision mesh constructor and the Octree constructor, because I'm going to be writing some code in both of them for the rest of this video. So the main thing that I'm going to need the Octree to do is be able to subdivide itself. So I'm going to define a method. We're going to call this static split. This is going to be a function which is going to take a single parameter, which is going to be depth. Contrary to what the syntax highlighting would have you believe, this is not going to be depth related to the GameMaker room editor. This is going to be a recursive function, and this is why I said I was strongly considering making a video about recursion before I did this, but I have not, at least not yet, so bear with me. First, I'm going to check for a base case. This is going to be if depth equals 0. I'm just going to say return. Anyway, the depth value, this is going to control the number of subdivisions inside an octree. I did mention that you can do this recursively as many times as you want. We are going to, when we initially split an octree, we are going to do it, for example, we're going to tell it to split itself into 3 levels. Depth refers to the level. Each time we are going to subtract 1 when we go down a level. And if depth hits 0, then that's going to be our signal to stop. Next, and these next 2 things are just going to be little safety checks. If array length self.triangles equals 0. So if there happen to be no triangles in part of an octree, when we try to split it, we are going to not do anything. We are simply going to return. And if self.children is not equal to undefined, we are also going to return. We are going to be assigning a value to self.children in this method, and if you have already split an octree, we will not be allowed to do it again, because that will cause some pandemonium, which we do not want. So next, let's define a few local variables. One of our center is going to be self.bounds.position. This is the center point of our axis line bounding box, representing the bounds of our octree. Next, var sides is going to be self.bounds.half extents. These 2 values are essentially the 2 important pieces of information that make up an axis line bounding box. I'm saving them to local variables now because we're going to be referring to them quite often. But I also want one more thing, which is to divide self.bounds.half extents by 2. We're going to be using this information to construct the inner octrees for each split of the octree, and we want the side length of the inner octrees to be half of the originals. You can divide it by 2 if you're one of those people. You know who you are. You can also multiply by 0.5. It doesn't matter. So let's create the inner octrees. Those are going to live in an array which is going to be contained in the self.children value. So I can define an array for this. You can use an array literal. This is going to be the second block of very tedious and repetitive code that I'm going to be typing out in this video. If you want to just copy and paste from my GitHub repository into your own project, I would not blame you. First is going to be new call octree. Call octree takes a bound, which is an axis line bounding box, so we're going to say new ab, new call ab. The position, the central position of this is going to be center.add. So this is going to be the central vector 3, and we're going to add some values to it. We're going to add approximately half of the side lengths of the original bounding box. So we can say, and unfortunately we can't just make this as easy as center.add sides or whatever, because the different octrees that are going to be in the different subdivisions are all going to be slightly different from each other, so I'm going to need to say new vector 3. And this is going to contain a few things, for example, negative sides.x. I'm going to leave a couple spaces so that all my code lines up with all my other lines of code. Sides.y, negative sides.z. Let's see, that's the vector 3. Close parentheses again, that's the add method. The half extents are going to just be sides. And the call octree constructor takes one more parameter, and that is going to be self.mesh. Okay, that is one of the 8 subdivisions that we need for the Octree. We need 8 more of these. 2, 3, 4, 5, 6, 7, 8. So again, this is going to be very tedious. I am going to refer carefully to my notes. In fact, I think I'm going to just copy and paste out of my notes. What happened? GameMaker? Anyway, copy and paste fails aside, this is what the code looks like now. You can see that each of the inner subdivisions now contains an octree of its own, offset from the center of the original octree by half of the bounds in 8 different directions. So 1 to the left, 1 to the top, 1 to the front, left, so on and so forth. Again, if you want to just copy and paste this code from my GitHub repository, I would not blame you. If you want a quick sanity check, the signs on the side XYZ going down goes minus, plus, minus, plus, minus, plus, minus, plus. On the Y, it's 4 positive sides dot Y and then 4 negative sides dot Y. On the Z, it is minus, minus, plus, plus, minus, minus, plus, plus. And all the other lines are more or less identical. They all take the same mesh as their inner mesh. They all take a collision ab into the Octree constructor. Okay, so now that we've initialized all of the inner Octrees, we need to actually populate them with triangles. And to do that, we can say for var I equals 0, I is less than 8, I plus plus. If you do not wish to have a free-floating magic number in here, you can use, instead of 8, array length self.children if you wish. I do not particularly think it matters in this case. It's not like you're ever going to have anything other than 8 in an Octree subdivision.
Hey.
We are going to deal with each of these inner Octrees in turn. I'm going to say our tree is going to be self.children stored at index I. And then for each of the triangles stored inside the Octree that we're splitting, so for var j equals 0, j is less than array length self.triangles j plus plus. First, we're going to check whether each of these triangles in our main Octree that we're splitting is located within the bounds of each of these subdivisions. We can say if tree.bounds.check triangle self.triangles index j. And since the bounding box is simply a collision ab, since the bounding box is simply a collision object, it also has access to each one of the collision checking functions within it, collision checking methods within it. So we can say if the tree.bounds.check triangle of each triangle in the Octree, then we can array push tree.triangles, and the triangle is going to be the data that we're going to push onto the triangle array is just going to be a reference to that same triangle. If constantly using the array push function here bothers you, hopefully soon it will bother you less, because Yo-Yo Games is eventually going to optimize the array push function to make it much faster. You can also essentially do 2 passes over the triangles array, one to figure out which triangles are inside it, and another to actually populate it with each triangle. And then you can initialize the triangles array with something like this, and then you can do another loop over to actually populate it with the values. But honestly, since that's going to involve double the number of triangle collision checks, it's probably not going to actually be that much faster. Anyway, this code is going to run for each of these subtrees, and then once you have populated each of these subtrees with the triangles that are contained within them, we can say tree.split. We can recursively call the tree.split method with depth -1 as the depth value. If you do not include the -1, you will have an infinite recursion on your hands. Your game will never start. If for whatever reason you find your game behaving strangely, if you find your game hanging or getting stuck in an infinite loop otherwise, you might want to check to make sure that your I's and J's are in the correct places, that you're using like the correct loop counters in both of the loops and that kind of thing, and that you're not using the wrong one. That's another cause for infinite loops. And is there anything else? So once you split a node, we don't really have a need for our own triangle array. If you want, you are free to just set the original triangle array to empty array or something like that, or you can set it to undefined. But it's there's no real harm in just leaving it there. Again, in Game Physics Cookbook, which is targeting C++, which does absolutely nothing to manage your memory for you, Gabor Sauer would have you manually deleting your original triangle array at this point, but since GameMaker does a lot of things for us, we do not need to worry about that. Another thing that you do not need to worry about that you will find in Game Physics Cookbook, by the way, is a function to delete an octree. But since there are no dynamic structures in here, no anything that needs to be manually deleted, this is just structs and arrays, we do not have to worry about that. So now if I run the game should run and it shouldn't crash or anything like that. If I were to hit the M key and construct a triangle mesh, nothing is actually going to happen because I'm not actually doing any splitting of the triangle mesh in the first place. So let me say self.accelerator.split, and I'm going to go with 3 levels deep. This is in the ColMesh constructor right after the original Octree has been created. Let me try running the game again. We're going to see that the game is gonna take a couple seconds, and then after about 2,000 milliseconds or 2 seconds and change, we're going to have a tree popping up. And there was... How long did it take to instantiate a mesh shape the first time? About 3 milliseconds, and now it's almost 1,000 times that. This is because we are doing an awful lot of computation up front to sort each of the triangles in the collision mesh into an octree. This is fairly computationally expensive up front, but as we're going to see later, it is going to speed up collision checks of all types against the octree by a solid amount. So that's the last thing that I wanted to do in this video. I am going to commit this change. We can commit split an octree into subtrees. I'm going to add just a little tiny bit more debug code to draw the bounds of not only the original bounding box of a triangle mesh, but also the bounding box of every octree inside it. So let me find my test code. That would be self.data.accelerator, and we're going to call debug draw on that. So let me start that again. Let me run the game again. Let me instantiate a mesh again. That's going to take about 2 seconds. If I were to hit the tab key, we can see that there's a little more going on there. If I were to zoom in and hit the tab key, you can see that we have subdivided the original bounding box into many inner bounding boxes. You can also see that the denser parts of the tree have more subdivisions. So the outsides of the tree that do not have any triangles in them, we have not bothered to split these some of these outer blocks further. But for example, the top of the tree with all the leaves, there's a lot of triangles in this space. We have gone all 3 levels deep in here. If you wanted to, you could split the tree. Where are we? You could split the tree further. You could split it to, for example, 4 levels. In this case, it's not really going to make a difference because each and every one of the triangles in this tree object are large enough that by 4 levels deep, it's probably going to occupy more than one subdivision in the octree anyway, and it doesn't really. It's just really going to be a waste of time. You can see that it is taking longer to draw this debug bounding box because there's so much more of it now. You can see out in the console that it took about twice as long to subdivide it at 4 levels down than it did at 3 levels down. On the other hand, if I were to only split 2 levels, and that might honestly be enough for this tree model, but if I only split 3 levels down, it is going to be much faster to do, but the tree itself is not going to be nearly as dense. Okay, that's a visualization. So I'm going to commit this change. And that's going to do it for me for today. Next time, we're going to actually use this data structure to do faster collision checks against each of the shapes that we previously defined. And also, hopefully I'll have time for this. Hopefully it won't run as long as this one did. We'll also do the raise and line collision checks against the Octree. That should be a fun time. So, my name is Michael. I like wizards and dragons and making games. I have a Patreon, so if you want to contribute towards these videos being made, check for links to that in all the usual places. You can see some fun things like your name in the credits, or hearing a verbal shout out of yourself at the end, or about once a month I post a preview of my future plans. And if you wanted to pledge, I would definitely appreciate it. Otherwise, if you want the code for this, look for the GitHub repository down in the video description. Hopefully I will actually remember to post it this time, because in the last couple of videos I forgot about that for quite a while. But like I said, some of this is fairly repetitive, and if you wanted to copy and paste out into your own project, I would not blame you. Otherwise, I try to post 1 or 2 game dev videos a week, so if you're interested in any of that, feel free to subscribe. I hope you all found this useful, and I will see you all later. By the way, since this is a very cool visualization, if you're wondering what this looks like with a larger model, and this may take a few seconds, because it's a rather big file, I want to say this is about 5 times as many vertices as the Kenny tree. Here is the Going Merry, and here it is subdivided into an Octree. I think it looks nice. Okay, hello all you crazy people out there. My name is Michael. I like wizards and dragons and making games. Welcome back to 3D Collisions in GameMaker. Last time I went and implemented a little data structure on triangle meshes that will allow us to do collision checks against them much faster than by just checking each triangle individually. And today we're actually going to be making use of that. So last week was Octrees. As usual, standard disclaimers apply. This is part of a long-running series of 3D Collisions in GameMaker videos that I've been making. If you have not seen any or all of the previous videos, I recommend going back and doing that, because this is going to build on a lot of it. Let's get started. So this is what our Octree structure looks like up close. You can see, I really like how this looks visually. I don't know if I'm just weird or not. The code for the Octree looks something like this. The important part is subdividing it into pieces so we can split an Octree to a certain depth. Today we're going to be mostly ignoring that. In fact, I think I will go back to a single pane code editor, and we're going to actually be using this to implement collision checks. So the high-level goal of an Octree, and indeed most other collision data structures that you can use, is to eliminate triangles from collision checks if you know that you do not need to collide with them. And for example, if you know that a 3D object is only going to collide with a tiny corner of a triangle mesh, Octrees allow you to only check for collisions with triangles that are actually in that corner. This is why we sort them into the hierarchy. And the first step towards figuring out which triangles need to be checked for collision against an incoming object involves figuring out collision checks with the Octree itself against the incoming shape. Just as splitting an Octree involved recursion, we can also use recursion to figure out which inner Octrees are colliding with the incoming object. I'm going to be going with the collision sphere just for now. But in this particular case, I personally think an iterative solution is more than adequate. Recursive solutions for this sort of thing exist, and if you really like recursion, you can go and do that, but I'm just going to be using a good old while loop for this. So let me start off with an array. I'm going to call this array process these. And it's going to be initialized to not an empty array, but it's going to be initialized to one element. The element is going to be our root Octree. If you like, you can use a DSQ for this, because we are going to be treating this like a DSQ, but I'd like to use the built-in GameMaker data structures as little as possible for this. I think I actually haven't used any at all. Yeah, no hits in this entire code for any GameMaker data structures. Anyway, we are going to do a little while loop, and that is going to be while array length is where array is greater than 0. Then we're going to do something. This is a while loop. This is going to run for as long as this array has elements in it, or until a collision is detected. If you are not careful with this, and if you do not write this code correctly, you can end up with an infinite loop, so be careful with that. First, I'm going to say our tree is going to be process these stored at index 0. We are more or less going to be treating this array as a queue. We are going to add values onto the end of it, and we are going to remove values from the beginning of it. So we are going to get whatever element is at the front of the array, and we are going to save it to this variable of our tree, and then we are going to array delete a value in the array, process these at index 0, and we are just going to delete one element. So depending on whether or not this tree that we're getting from this the first position in this array actually contains other octrees, whether or not it's a parent node, or whether it doesn't, whether it's a leaf node, we're going to do different things. So if tree.children equals undefined. So if this is a leaf node in data structure parlance, and this if this octree does not have any more subtrees, we're going to do one thing, else we are going to do another thing. I'm going to start with the else condition here, just because I think it makes a little bit more sense, because it's going to involve pushing the subtree onto the list of octrees that we want to process. To do that, we are going to loop over each of the I is less than 8, I++. To do that, we are going to loop over each of the inner children trees. We are going to say if tree.children index I dot check sphere with the incoming sphere. Then we are going to array push onto the process these array. We're going to push tree.children index I. So if this particular branch, if this particular subtree is also in collision with the incoming shape, then it is possible that there are triangles within that subtree that are colliding with the incoming shape, and therefore we want to save it to the array so that we can process it later. These nodes that we are pushing onto the octree have the potential to contain triangles that are colliding with the incoming shape. Otherwise, if the subtree that we're checking does not contain any child nodes, we are simply going to loop over for our I equals 0, I is less than array length, and just like in the last video, I should probably mention I am not writing perfect machine code optimized code here. I am writing code that I think is easy to read and easy to figure out what it's doing. Writing 3D collision systems in GML is definitely one of the rare places where micro-optimizations can actually make a difference. I am increasingly interested in making another video in the future that's just about micro-optimizations on this code, but that is for a day that is not today. Anyway, we are going to loop over every triangle in tree.triangles, I++, and then simply we're going to check each of these triangles for collision with the incoming shape. If tree.triangles index I check sphere against the incoming sphere, then, well, that's a collision. Our job is done here. We can return true. And if by the end of this big giant while loop no collisions have been found, that means that no collisions exist to be found here, and we can return false. Okay? So let me run the game now, and let's see if I actually got this all correct on the first try. Sphere is going to be shape 1, and that said check sphere variable not found before reading it, and I believe that is because instead of using tree.children.checksphere, I need to do tree.children.checkbounds.checksphere, because this is an octree object. That's one of these. This does not contain a checksphere method, but the bounds is an access line bounding box that does contain the checksphere method. Let me try that again. All right, M is going to create one of those. One is a collision sphere. Right off the bat, we have shapes overlap being detected. If I were to move the collision sphere out, we can see that right about here, and I can't get it pixel perfect because I don't have a high degree of precision over where the sphere moves, where these shapes move, but we can see that about here, the collision stops being detected. On the other side, same distance, collision stops being detected. If I were to, what's my controls? If I were to move the camera out a little bit, and move the sphere up, we can see that once it hits the leaves, we have a collision being detected. Obviously, in the middle, we have a collision being detected. Perfect. All right, except for that one typo, I got that right on the first try. Wonderful. So you can see this is performing considerably better than it was before. Off the top of my head, when I was testing this earlier, axis line bounding boxes versus triangle meshes were giving me about, I want to say 15 frames per second. And spheres might have been a little bit better. Spheres might have been like 25-ish. You can see that now our FPS reel is hovering about 200 to 300. It's not amazing. Again, this is not perfectly optimized code. There are definitely some micro-optimizations that can be made that will shave off a couple CPU operations. Again, if we wanted to run this in the Yo-Yo compiler, I don't know if I should say again, I don't know if I mentioned that earlier, but if we wanted to write this in the Yo-Yo compiler, that's going to compile the game into C++. It's going to convert the GML into C++ anyway, and then compile to C++. And that should give us a further performance boost. I want to say such a thing should give us about a 2 times improvement in speed, and it's actually a fair amount better than that. We were getting 200, maybe low 300 FPS real in the GameMaker virtual machine, and we are now with the Yo-Yo compiler getting 6, sometimes 700 FPS real in the Yo-Yo compiler, which is a considerable improvement. See my previous rants about why FPS real is actually not that useful of a metric. Alright, that's wonderful. So if you want to, you can copy and paste this code and you can implement it for all of the other shapes. That is going to be a little bit of a pain in the neck. Copying and pasting code is generally a little bit frowned upon, especially when it's very, very similar code and it is maybe possible to come up with a general solution. So that's exactly what I'm going to do. I'm going to define myself a pneumatic static check general. That's going to be a function which takes any old incoming shape. Shape can be either a point or a sphere or an axis line bounding box or any one of these other things, except another mesh, really. And instead of on line 701 here and on line 707, instead of saying tree.triangles index I.check sphere against the sphere, we can turn that around and we can instead say shape.check triangle against the triangle stored at this position in the array. And down here on line 707, we can likewise say shape.check ab against tree.childrenindexi.bounds instead of doing a check sphere. And that is going to be our little general solution. This will work for any shape that has check triangle and check ab implemented, including other meshes. I recommend against it. Let's see. So what that means is that in checkpoint here, did I like... Oh, you know what? Alright. Almost moved the wrong code. In checkpoint here, we can say return self.check general against the point. In check sphere, we can say self.check general against the sphere. Same thing for the axis align bounding box. Self.check general against the axis align bounding box. When it comes to planes, when it comes to triangles.
Hey.
Meshes. I'm gonna say don't do this, but you know what? This is still not going to perform very well, even if it's accelerated, just due to the sheer number of math involved. But if you really want to, we can do a triangle mesh against another triangle mesh. Ray and line I'm going to leave for later. Those are going to be a little bit different because the raycasts are constructed a little bit different. I see we are building for the yo-yo compiler again. I'm going to stop that because the yo-yo compiler sometimes has issues when you run it more than once with code changed. I'm going to go back to the virtual machine. Let us create ourselves a tree, and let us go with a point. So checking points against triangle meshes is kind of useless because this only checks to see if the point is contained within each of the triangles. It does not check to see whether the point is inside the triangle mesh. Containment checks are a little bit different and also a little bit more difficult, and also a little bit, I'm not going to do that right now. However, spheres, as we saw earlier, spheres work. The general solution works for spheres. All right, that's awesome. Axis line bounding boxes versus triangle meshes. Let me move my mouse cursor over the way. We have collisions being detected up at the top, no longer. Over on the sides, we are barely cutting through one of the leaves of this tree. Out on the sides, we have collisions detected and not. And left and right. All right, great, wonderful. What next? Planes. Oh, that's a little triangle. All right, so we can also do individual triangles against triangle meshes again on the expensive side because triangle collision checks are on the expensive side. You can see that whereas the sphere was giving us about, let's say, 300 FPS real, this is giving us about a little less than 60. What was the AB giving us? That was giving us high 300s, sometimes 400. All right. The triangle still works, as you can see, if you move the shapes around. Ooh, wow. Well, that's still better than triangle, just iteratively checking every triangle against the tri-mesh. We're down to the 15s here. Anyway, what's next? Planes. Alright, I'm losing my controls here, but planes, check for a collision against the triangle mesh. That works. If I move the plane over the top of the tree, then the collision is gone. If I move the plane down below the bottom of the tree, the collision is gone. If I were to rotate the plane and move it around, it is colliding correctly. What other shapes are there? Lines. I do not like the way that I constructed my line tests, but if you were to... Oh, you know what? I didn't implement lines yet, did I? Alright, I'll do that next. Anyway, this is a fairly important milestone. I will be committing this. So first, raycast against collision meshes. This is going to look a lot like the other shapes against the collision mesh, in that we are going to make a queue of subtrees that we want to process, and then we're going to check each of the relevant subtrees for triangles against the ray. However, the raycast checks are just different enough from the other shape checks that a general solution is kind of going to be more trouble than it's worth. You could do it if you really wanted to, but it'll be ugly. So instead, I'm just going to copy and paste. There are two relevant lines that are going to need to change. Again, that is going to be here in the if tree.children equals undefined when we check each of the triangles against the incoming shape, in this case array, and also farther down in the else block, where we check the ray against the axis line bounding box that represents each of the octrees. For the first one, we can just use ray.checkTriangle instead, and since each of the raycasts collision methods use they take a second parameter for the hit info, so that we can use this to figure out relevant information about the point of contact, such as where it happened and what the surface normal of the thing that we contacted with was. When we say ray.checkTriangle, we are also going to pass in the hit info struct over here. We're also not going to return true, and the reason for that is because when you do a raycast, you generally want not only to figure out if a collision with the ray happened, but you want the information on the one that happened nearest to the ray's origin. So instead of just returning true, we are going to save the result. We're going to initialize hit detected to false. If you find a contact between the ray and a triangle, hit detected is going to be set to true. And also inside ray.checkTriangle, the raycast hit information struct is going to be updated. And then at the bottom, instead of returning false, we are going to need to process every triangle in the Octree. We're going to return hit detected. And then when we check the raycast against the axis line bounding box, we don't really care about the hit info, but the raycast.checkAB method would like a hit info anyway. You can do one of two things. You can either go into each and every one of the hit info, each and every one of the check raycast methods, and you can do something along the lines of if hit info is not equal to undefined, and then you're free to ignore the hit info parameter to the raycast function down below, or you can just not do that, and you can instantiate, where was I? Check right. You can instantiate a dummy raycast hit information struct, which we are never going to use, but is just going to be passed into the checkAB method to keep the code happy. Let's see. This should work. Am I missing a close parentheses anywhere? I need... Alright, I am. Parentheses was in the wrong place. That should do it. Now, when I instantiate a triangle mesh, and if I were to zoom in and put my mouse cursor over it, you can see we have a raycast against the tree, against the collision mesh, and it's running at a solid at least 200 FPS real, depending on where you do the raycast into a more sparse or more dense part of the collision mesh. It may perform better or worse. That's the case for all of the collision shapes, but it's probably more apparent with the raycast. And you can see that the correct hit location is identified, the correct surface normal is identified, and we are also identifying the triangle that is nearest to the camera, as it should. Okay, and lastly, how do you detect collisions with lines? This is going to look an awful lot like some of the other line collision code, in that we are just going to use the check raycast as basically a springboard. We're going to turn the line into a ray. We're going to figure out if the ray hits the mesh at some point between the start and the end of the line. That's fine. So now if I run the game, we should, and despite the fact that which one was it? There we go. Despite the fact that my line collision detection test code is not very good at all, we can see that we do indeed have collision between the line and the triangle mesh. Alright, that was pretty easy. A lot easier than last time, honestly. Okay. That was fun. So we now have collision detection between triangle meshes and other things performing pretty well, all things considered. I still recommend not doing collision checks against triangle meshes if you can avoid it. If you absolutely have to, against, for example, terrain or a very, very strangely shaped building or something like that, then you can. Definitely would recommend using either a sphere or an axis line bounding box or a plane or something simpler if you can get away with it. Capsules are very common to represent things like the player and NPCs. I have not done capsules yet. I do want to later. I just I consider the other shapes a little more important because you can generally fake capsules with either two spheres or two spheres and an ab or something like that. There are other shapes that you might want to do. Cylinders, cones, oblique bounding boxes, also known as oriented bounding boxes, just abs with rotation, are definitely something that I'd like to cover eventually, for reasons that are hopefully obvious. There's also the matter of applying a transformation to a triangle mesh, and I suppose applying transformations to other shapes before doing collision checks with them so that you can have things such as objects that move around the world colliding properly, but I'll take care of that later. That may or may not be what I decide to do next. And lastly, if you're wondering if you can apply the same Octree logic to not only triangle meshes, but also just groups of other collision objects in general. So if you wanted to, for example, have a collection of abs in a game world, and if you wanted to sort those into an Octree, the answer is absolutely yes, you can do that. And that's another thing that I want to do eventually, creating actual collision worlds that are more complex than just lists of collision objects. Anyway, I did both this and the Octree video, last week's video, in one shot, and my voice is seriously starting to die today, so I think I'd better stop. My name is Michael. I like wizards and dragons and making games. If you want the code for this, look for the GitHub repository that I have been committing to in the video description. Look for I believe it's going to be week 17 using Octrees release. I'll have a link to the particular branch as well. I have a Patreon, so if you want to contribute towards these videos being made, there are links to that in all the usual places. You could see some fun things like your name in the credits, or hear a verbal shout out of yourself at the end of each and every one of these videos. I post a list of my future plans about once a month, and if you wanted to pledge, I would definitely appreciate it. Otherwise, I try to post about 1 or 2 game dev videos a week, so if you're interested in the weirder things that you can do in GameMaker, such as 3D collisions, feel free to subscribe. I hope you all found that useful, and I will see you all later. I forgot to include this demo again, so if you're wondering how the collision detection scales up with larger models, I want to say the going Mary is about 2,500 triangles compared to the Kenny Tree's a little less than 500. So if you're wondering how this performs when doing collision checks against other shapes, you can see it is a little bit more expensive, definitely. We're getting a very variable amount of frames per second based on where in the mesh we're checking for collision with the axis aligned bounding box, but it's still definitely a lot better than when we were just looping through every single triangle. Worst case seems to be about 40-50 FPS real mesh against an AB, whereas best case scenario we can do a lot better than that, 100 plus, 200 plus, depending on where you're checking, which leaves of the Octree you're checking. I would expect to see more or less the same thing if I were to use the sphere, and we do. Okay. Other things you can do to optimize collision performance I will talk about later on in the series, but in the meantime, this is certainly at least serviceable. Hello all the crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. So last I left off, we had just finished implementing fast, or at least fast-ish, 3D collisions against triangle meshes, which I think are the part of 3D collisions that a lot of people were expecting when I said I was going to do this. It only took like 18 videos. And today we're going to start looking ahead to creating entire 3D collision worlds. So I think I said at the end of the last video that I was thinking about doing matrices or something this next time, and I decided to hold off on that. Matrices are kind of their own whole entire thing, and in any case, they're probably going to be used mostly in things that I'm going to be doing a lot later anyway. So instead, let's do something relatively easy. So a lot of you have probably looked at the Octree structure that we were using for accelerating triangle collisions, and you probably had the thought occur to you, it is probably reasonably simple and straightforward to apply the same practice of using an Octree to not only a triangle mesh, but to other shapes as well. And if that did occur to you, if you did have that thought, you are correct. And as it turns out, that is exactly what we're going to be doing in the coming weeks. At the moment in this here test world that I have set up, this entire world is just a big old list of various collision shapes, and it definitely performs better than a big old list of triangles, because pretty much anything performs better than a big old list of triangles. But at the same time, it doesn't scale super well. There's 1,000 objects in this world, and it would be nice if we had a way to organize all these into a hierarchy as well, so that we didn't have to go to the effort of checking collision for the player against things that are way off in the distance. And in very much the same way that we did with the triangle collision meshes. But first, before we deal with that, there is a little bit of extra housekeeping that I would like to get out of the way. So right now, we have just a collection of individual collision shapes that we are checking against each other. It would be really nice if we could instead have a single type of collision object that we could use for all shapes and treat the same way, without having to say, for example, sphere.check ab or ab.check plane or whatever. We don't need to know which types of shapes we're checking against each other. All collision types are just going to be treated the same way. As you can imagine, if you have a big game world of 3D objects that are all interacting with each other, there's a good chance that some of them are going to have different collision shapes than others. You might have a couple planes, you might have a couple spheres, you might have a couple later on capsules for things like NPCs and whatever. And it would be really nice if you didn't have to keep track of which is which, and you could just treat all objects the same way. So the thing that I'm trying to avoid, if I were to go and create myself a new script, and I'm going to call this call_world, because that is what we're going to be working towards. You could do, and this is what I'm doing my best to avoid, is to have a single function that's like check anything, and it'll take two shapes as a parameter, shape1, shape2, and what it'll do to figure out which collision detection functions it needs to call is something like hello, GameMaker. If instance of shape1 equals call point, return shape2 dot check point shape1, and then if that's not the case, if the instance of is going to equal call sphere, call the check sphere method on it instead. Yeah, this is what we don't want to do. Even if you don't use the instance of function to like get the name of the actual like struct constructor, which is awful in many different ways. Maybe you might attach like a, I don't know, a type variable to each collision shape and check that instead. Regardless, we are not going to be doing that. I really don't like having to hard code things like that, and we're going to be coming up with something that is at least in my opinion a little bit more computationally elegant. The second thing that I'm going to want to account for in the near-ish future is being able to reference back to the either the GameMaker instance or another game object that is represented by a collision shape. So right now, we have our loose collection of collision shapes, but they can't refer back to any game object, so you can't collide with, for example, you can't collide with an axis-aligned bounding box and say, okay, this is a tree versus, okay, this is a house, or, okay, this is a, if you were to get really fancy, this axis-aligned bounding box represents a collision zone, which once I step into it, it should teleport me to another part of the map or something like that. We don't have anything like that right now. And it would be really nice if we could. You could fix this by just adding to the constructor something like, in addition to the usual parameters of position and radius and whatever, you could add another parameter that's like reference or something like that, and then self.reference equals reference, set it to a struct variable, and then when you somewhere else in the game try to instantiate a call sphere or something like that, you could say new call sphere, position, radius, whatever those happen to be, and then the reference could be like self.id or something if it's a GameMaker object or whatever. That's valid. There's nothing really wrong with that if you wanted to do it like that, but I'm not going to anyway, because the solution that I'm going to come up with for the first problem is going to apply to the second problem as well. Similarly, when we do get around to doing matrix transforms on shapes, it's going to be nice to be able to attach a transform matrix to each and every one of these shapes. And again, you could attach that data to each shape as a parameter to its constructor. I'm not going to. You might also want to do something to the effect of allowing the programmer to filter collisions against each other, so that you can detect collisions with certain groups of objects but not others. And once again, you could pass that as a parameter to the constructor, but what I'm going to do instead is hopefully a little bit more all-encompassing, and that is going to be creating another struct, which is a wrapper for these shapes, which is going to be function, I'm going to call it call object. And this is going to take a few parameters to its constructor. One is going to just be the shape, so any given point or sphere or ab or whatever, so there's just going to be the shape that we're using. There's going to be the reference, which is going to be an instance ID or a reference to a struct, which represents the player or a non-PC or whatever. And that's actually going to be it for now. I will attach the other things that I mentioned later on. If you've used P3DC in the past for GameMaker, precise 3D collisions that someone wrote way back in the GameMaker 8 days, you've probably seen a concept similar to this, being able to attach a user ID or some other type of reference to an object. If you've used the Venomous Bullet DLL for 3D collisions, that's a little bit more recent. That's basically a GameMaker wrapper for the Bullet physics library. Same thing. So let's get down to business. I'm going to define myself a method. I'm going to call it static check object. Is going to be a function. This function is going to take one argument. It's going to be another object, like this. This is going to be the only method that this struct has for checking for collisions against other object types. We're also going to have a separate method for static check ray is going to be equal to a function which takes a ray as an input parameter as well as a hit info struct, which we have been using to collect additional information about raycast hit detections. But otherwise, that's going to be it. You could make the argument that you also want to do static check line as a sort of supplement to the raycast, but I think for most practical purposes, you could get away with treating a line cast as either an object or a raycast, depending on what you need it for. So I'm going to not include it today for the sake of time. And if you would like to do it yourself, you hopefully have the knowledge to do it yourself without too much trouble. So this, on its own, doesn't really solve the problem of needing to figure out which types of objects you're checking for collision against each other. It kind of just kicks the problem that I posed at the beginning of the video down the road a little bit, and you could very easily just do it here if instance of object dot shape equals whatever. You could just do that here, but we could also go back into the call shapes script and define a couple of additional methods, or really I should just say one additional method in a couple of different places. This is going to be static check object equals function. It's going to take an object as a parameter, and it's going to just be one line of code, return. And remember, these objects, these call objects, they have an existing collision shape as one of their instance variables, so we could just say return object.shape.checkPoint against self. And this might look like it doesn't really accomplish much, but since each collision shape already knows what it is and doesn't have to be told by you, the programmer, you could take any old object, whether that's an object containing a sphere or a plane or a triangle mesh or whatever. You could take any old object, you could look at its shape property, and you could say whatever that object type is, we're going to be checking for collision against a point, and that point is going to be ourselves. And this does away with the need for an entire big if-else for checking the type of each individual shape. And once we implement this particular method for all of the existing collision shapes, so the sphere is going to do the same thing, but instead of saying object.shape.checkPoint, we're going to say object.shape.checkSphere. Same for the axis aligned bounding box. Same for the plane. And since you probably don't need to see me typing that out for every single collision shape, I just went ahead and did that. You can see the changes here. I did it for every collision shape type except for rays. Rays are special. Rays are going to be dealt with on their own. That includes collision line, by the way. We have a collision line check object as well. So if this is a little bit too object-oriented happy for your taste, because I know that some people like object-oriented programming like a lot, and then there are some people who think that object-oriented programming is the worst thing ever, and you should never ever use it if you don't have to. You could go and do, in the collision object.checkObject, what I said I was trying to avoid at the beginning, and just do a big if-else tree. It would work, and the end result will be the same as what I'm going to get here. It's just, I just get nightmares thinking about big if-else trees like that, and I'd rather avoid it if I can.
Hey.
So now when we want to detect collision from one object to another, we can simply say return self.shape.checkObject against the other object, and we're good to go. So there's one thing that can happen sometimes if you're dealing with a big Super Mario 3D collision world, and that is that you try to accidentally detect collision with one object against itself, and as you can imagine, if you try to do that, you are 100% of the time going to say that these two objects are colliding, assuming that you've implemented your collision checking math correctly. And most of the time that is not actually what you want. You don't want the player to detect collision against themselves, for example. You don't want an enemy's collision box to detect collision against itself. That would be a little bit unfortunate. So I'm just going to add an additional check at the top of this check object method that says if object equals self return false, just to ensure that that will never happen. And there's a few other things that you might do that are similar to this line that you can do to fend off collision checks before they happen, such as I mentioned earlier, collision filtering using masks, but I'm going to get to that later. I was already hoping this video would be a little bit on the shorter and simpler side, and it's already taken longer than I thought it would, so... Anyway, coming down here to the check ray method, this is going to be pretty similar. We're going to say self.shape.check ray against, instead of just any other arbitrary object, we can do the ray and we can do the hit info. We don't have to do the fancy like object-oriented tricks to have each collision shape detect the proper collision against the object because we already know the shape of one of the inputs here, and that is the ray. We can just say whatever shape happens to be contained within our object, we're just going to check it against a ray, including the hit info struct. So in a few weeks, when I get around to doing another 3D Collision World demo like this, each of the individual objects that are in the scene, whether that's the player or all the trees or the floor, these are going to be represented by collision objects, which contain a shape, rather than just individual shapes that are scattered around. Also, as I mentioned, right now the collision detection in this demo, if you recall, is just handled via a big ol' list of collision shapes, and we are also going to be organizing that into a hierarchy to make it a little bit more efficient. You can see that with 1,000 trees in the scene, things are starting to slow a little bit to a crawl, which we do not want. Simple shapes like cubes and spheres and whatever are definitely better than checking for triangles, but again, if we can make this whole thing perform better, we should definitely do that. So I'm going to leave this here for today. Hopefully you understand why these 13 lines of code plus whatever I added to the shapes file, why these are important, but also at the same time it shouldn't be too difficult because, again, the last couple of these 3D collision videos have been on the complex side, and I'd like to once in a while make something that's not quite as complicated. And also I'd really like to spend less than like 6 hours editing one of these videos one of these days. Hey. Between you and me. Next time we're going to organize a bunch of objects into a collision world, and then after that it's time to bring it into a demo world. So, my name is Michael, I like wizards and dragons and making games. If you want the code for this, look for the GitHub repository down in the video description. Do I want to try to break this up into 2 commits? Yeah, sure. GitHub Desktop recently in an update added a little warning in case your commit message goes over 50 characters, and I feel like it's personally judging me ever since it started doing that. Specifically look for the I'm not trying to do that. Specifically look for the 0.18 release for this week's progress. I've been slacking on making each and every one of these things an individual release. I've been trying to get more on top of that lately. Anyway, I have a Patreon, so if you want to contribute towards these videos being made, look for links to that in all the usual places. You could see some fun things like your name in the credits, that sort of thing. About once a month I make a future plans post. And if you're pledged, you can see what videos I'm hoping to have out in the next few weeks. Otherwise, I try to post about 2 game dev videos a week, one tutorial like this, and one let's make a game. Currently that is a bullet hell. I hope you all found this useful, and I will see you all later. Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. So the last video in this series was a little bit on the short and not so complicated side, at least I hope. And it was all about working out a system so that any 2 arbitrary shapes can detect collisions against each other without having to have any knowledge of what type each shape is. And I said that was going to be very nice to have when it came to organizing a bunch of collision objects into a single game world, and that is what we're going to be doing today. So I've said something a few times about how the acceleration structure that I wrote for triangle meshes is going to be a little bit, if I can find an appropriate level of zoom here, a little bit similar to the acceleration structure that we are going to be using for the collision world as a whole. And that's what we're going to be doing today. We are going to be taking the concept of the octree and applying it to not just a triangle mesh full of a bunch of triangles, which are expensive to compute collision detection against, but to the game world as a whole, so that we don't have to deal with checking for collisions between 2 objects that are completely on the other side of the map from each other. It's not going to be the same, so if you go into ColMesh, the octree that we're going to be using isn't just going to be copy and paste from the from the collision mesh to the collision world, but it's going to be pretty similar. And if you were paying attention during that video, then this one is hopefully not going to be that complicated. So let me start by going into the call_world code file and defining another struct. I'm going to say function call world. And let's see, I'm going to give this a few parameters. One is going to be bounds min, another is going to be bounds max, and a third is going to be max depth. And this is going to be a constructor. Before I begin, I would especially like to draw attention to the fact that I pulled inspiration for this video series from a number of different sources. Game Physics Cookbook being probably #1 among them. But there are plenty of other philosophies that people have about 3D collision detection, and more especially how to organize such things into a single world data structure. And what I've worked out for this video is going to be what I, one, think is going to be easiest to explain, and two, what I have found works best for purposes of 3D collisions in GameMaker. I'm going to try to make a point to point out different places in this code where people might use different philosophies. That statement has been true for pretty much this entire video series, but there are many, many different ways that you can organize collision objects into a world, and some of them might look very different from this. So I figured I should draw special attention to it now. So let's get into this. I'm going to define a few things. One is going to be self.bounds. This is going to be the boundaries of the collision world. I'm going to say bounds equals new call ab from min max. The minimum and maximum values are predictably going to be bounds min and bounds max. So speaking of different ways to approach this problem, you might prefer, instead of defining a collision world with a set size, bounds min and bounds max, you might instead want to initialize the collision world with an array of objects and then calculating the bounds from there, the way that we did with the triangle mesh. But I'm going to instead opt for a system that easily allows you to add and remove objects during runtime. And initializing the collision world to a set size ahead of time is going to make that a little bit less work on our part. Next, I'm going to say self.acceleration structure. Self.accelerator is going to be initialized to... Oh, let me check my notes. I'm going to call this a new call world node. This is going to have a lot in common with call Octree, and in fact, I might actually just copy and paste the code and make modifications to it from call Octree instead of writing it over from scratch. There is going to be a lot in common. The parameter list I will not worry about for now. I will fill that in later when I actually get around to implementing the world Octree node. And then self.depth is going to be set equal to max depth. Depth. I hate the PTH sound in English. It's the worst. Now let's define some methods. We're going to have a couple easy ones. So static add is going to be equal to a function. It's going to take an object. I'll fill that body in later. Similarly, static remove is going to be a function. It's going to take an object. One of these is going to deal with adding an object to the collision world. One of them is going to deal with moving it. I'll let you figure out which is which. Next, static update is going to take an object. This is going to be when, for example, an object moves and you want to update its position in the hierarchy. I'll do this one right now. This is going to be a simple matter of self.remove the object and then self.add the object. So to update something's position, we are just going to remove it and then we are going to re-add it. Nice and easy. Next, static check object is going to be a function which takes an object. And this is going to perform a collision check between one object and all the other objects in the collision world. And the partner method that goes with check object check ray is going to be a function which takes a ray. And considering right now, do I want to actually pass a hit info into this check ray method like I do with all the other ones? Or since this is kind of like the like the granddaddy of all the check ray methods that we're going to be using? Do I want to just like create a hit info struct and return it as a result of this method? I think I'll actually go with the latter, because that would make it a little bit easier to use this system in development. Okay, so let me go create myself a new branch on GitHub. So this is going to be week 19. I am going to bring my changes over, thank you. And this commit is going to be defining the collision world structure. All right. Now let's talk about call world nodes. So I said I was going to do some copy and paste. Let me copy that. I'll paste it into the same code file here. So again, same deal as with the collision mesh structure. This is going to be a recursive data structure, a recursive Octree structure, and we're going to split it to a certain depth, and we're going to put things inside each of the subdivisions. So let's see what we have to work with here. Okay, so instead of instantiating an Octree and then like immediately splitting it the way that we did in the mesh Octree system, I'm going to name this something else. Let's call this call world node. Okay, I called it node the first time. I guess for consistency's sake, we could call it call world Octree like that. Consistency is a good thing, right? So the two arguments that the constructor is going to take is going to be the bounds. So that's an axis aligned bounding box representing the bounds of the Octree node. And instead of a triangle mesh, let's go with a depth. And update the names of all the variables in question accordingly. Instead of having an array that's called triangles, I'm going to create an array called contents. And that's not gonna, it's gonna serve the same purpose, but instead of just only dealing with triangles, and thus the array being called triangles, we're going to be containing a bunch of different collision objects. So I'm just going to call this contents. I guess if you wanted, you could call it objects as well, but in my notes I called it contents, so I'm gonna go with that. Children, these are the subtrees. So any inner octrees that this is gonna contain will be in here. This will be an array. Debug draw, I think I can get rid of that because I think I demonstrated how that works the last time, and I don't think I really need it anymore. The split method, and I suppose I can collapse the asset browser on the side of my screen so that you can see the whole thing. This is going to have a few changes. One, depth is no longer going to be a parameter because that is going to now belong to the Octree node itself. I suppose if you wanted to, you could go back and like rewrite the old Octree node code so that it would work the same way, but no big deal. If array length self.triangles equals zero, we're going to return. Same thing here, except instead of triangles, it's going to be contents. If self.children is not equal to undefined, we're going to return, and we're not going to do any splitting because this node already has been subdivided, and we don't need to do it again. Calculating the center, calculating the side length. That's good. Initializing the array of children, of the child octrees. That's going to be good. We don't need to make any changes except that we need to update the name of the struct that we're instantiating. So call world Octree like that. And at the end, so that our the arguments that we're giving it match the arguments that are expected. Instead of passing in self.mesh as the second parameter, because we no longer need that, we can say self.depth -1, so that we know what the depth of each subtree is. It's going to be 1 less than our current depth, so you can't subdivide an octree infinitely. And then down here at the bottom, after the array of children has been created, we're going to do something similar to what we had before. For each subtree, we are going to loop over the contents of our own octree, and we are going to say tree.bounds.checkTriangle. So this line here, this is where we're going to start diverging a little bit from the octree that we created for collision meshes. If tree.bounds.check triangle, then array push the triangle onto the subtrees triangle list, and then when you're done, split it again at a level of depth -1. First, I'm going to get rid of the split method there because, as I believe I've said, we're going to be only subdividing nodes in this octree when we need to, like when things are added or removed, and we're not just going to be automatically doing it for the entire tree at the beginning. Let's see. I also deleted this. These 3 lines here, this if statement. We're going to be implementing something similar, but it's not going to be exactly the same. For now, for the collision world octree, I'm just going to say I'm going to say tree.add self. And this needs to be contents instead of the triangles array. Self.contents index j. And again, this is going to be done recursively, and we will be defining some of these in a minute. So let me create the outlines for these next couple of methods. I'm going to say static add. It's going to be a function which takes an object as a parameter. Static remove. It's going to be a function which takes an object as a parameter. Static check object. And check ray. The check ray method for world octree nodes will take a hit info struct as a parameter, unlike the check ray method in collision world, because the collision world check ray method, as I said, is kind of the granddaddy of all the check ray methods that are in the system, and this will create a hit info struct that it uses and passes to each of the shapes that it checks, so that you don't have to do it yourself every time. Anyway, let's go with let's deal with the add method first. So, to start with, we will only add an object to a collision world octree node if object, and this is a collision object, not an actual shape, so we can say object.shape.check ab against the self.bounds. So first we're going to check the object against the axis align bounding box representing the size of the octree node to see if we're actually inside it, and consequently whether or not we should actually be added to it. You could put this in an if statement. I'm going to do kind of what I've been following, like code design-wise, and say if not object.shape.check ab self.bounds, we're just going to return, and we're not going to do anything. There's going to be a few cases which are going to cause us to exit out of various add and remove and whatever methods early. And I don't really want to chain that many if statements together. Likewise, if a collision object already exists within an octree node, we will not add it again. So you can only have one copy of an object within within one of these nodes. So we can do that by creating a loop for var I equals 0. I is less than array length self.contents. This is a pretty simple matter of looping over the contents array and seeing if it already contains the object. If self.contents index I equals object, then the object is already somewhere to be found in this this structure, so we can just return. And those are going to be the two cases that cause us to not add an object to an octree node. So then, assuming neither of those happens, assuming that we are within the bounds of the node, and assuming that we are not already within, like we have not already been added to the node, array push self.contents the object. So we're going to add ourselves to the contents list, and then if we need to, we can split the current node. So if self.depth is greater than 0, we can self.split, and this version of the split method takes no parameters. It'll just happen based on the properties of the existing node, and then we can recursively for var I equals 0, I is less than array length self.children I++, we can recursively add the object to each of the child nodes. So, and honestly, like, I knew that hard coding, like, for I equals 0, I is less than 8, I plus plus, was going to, like, make me uncomfortable in the future. A couple of videos ago when I did that for the, like, the triangle mesh Octrees. And, yeah, I wish I didn't. Nobody's complained about it so far, and now that I'm, like, calling attention to it, I'm probably going to have a handful of people just, like, making fun of me for it in the comments. But, yeah, let's not say I equals 0, I is less than a magic number, I plus plus. Let's actually use the length of that array instead. Anyway, that is adding an object to one of these nodes. Removing it is going to be similar. I'm not going to bother to check to see if the object that we are removing is within the collision bounds, because, for example, if you, like, change the location of a collision object, if you change the transform position of a collision object, and you move it somewhere else and you try to remove it after that, then, like, it won't be found and it'll just be sitting in the Octree node as sort of a ghost, which isn't really what you want. So instead, let's just do a for loop over the entire contents of this node. If self.contents index I equals object, this is going to kind of be the opposite of the test in the beginning of the add method. So if the object is found in the Octree node, then one array delete from our contents array index I one value, and also if self.depth is greater than 0, actually I'll just copy and paste again. And I'm going to need another loop counter. For j equals 0, j is less than the length of the children array, j plus plus, self.children index j dot remove the object. And then we can only ever have one copy of an object in in one of these nodes at once. So if we found it, that means there can't be any more of it, so we can stop searching, and we can say break. Actually, we can really say return, because that will end the method call entirely. Okay, checking an object against one of these Octree nodes is going to be pretty straightforward. One, if the object is not within the bounding box of the node, we can just stop our search right there, because we know that if the object in question is not within the bounds of the node at all, then that means it also is not going to be colliding with any of the things inside it. Strictly speaking, it can, because if you have an object within the node that's, like, sticking out of it halfway, you could still have a collision with that object even if you're not colliding with a node. But in that case, that object will also be contained within another Octree node, which does contain the collision shape that you're checking. So no big deal. So first, if self.children equals undefined, or I guess this would be synonymous with if self.depth is greater than 0, but I'm gonna say if children equals undefined instead, just in case we're checking a node that hasn't been split, because again, that won't happen until after things have already been added to the node. That's okay with the remove method, because if you get this far, you know that there's already been something added to the node. But so if our array of children nodes equals undefined, we can for var I equals 0, I is less than array length self.contents I plus plus. For each object that is in this node, we can if self.contents index I dot check object, and this is going to be where that nice, like, generic check object system is going to come into play. Checking object against the one in question, then we can return true. Otherwise, if the children array is not undefined, so if this node has been subdivided, we can say for I equals 0, I is less than array length self.children I++, and then if self.children index I dot check object, then we can return true. All right, these two, like both the if and the else sections of this branch look very similar. It's just a different array that we're checking. Whether or not we're a leaf node, whether or not we have subdivisions that we can investigate further, and there are ways that you can tidy this code up a little bit. You could just do a single loop over like a different array depending on whether or not we haven't subdivided, but not going to go that far. Anyway, if neither of these things return true, then we can return false. Because there is no collision with anything inside this node. And lastly, for check array, we can do something that's going to look pretty similar, and we can say a few different things. For example, instead of saying object.shape.checkAb, we can say ray.checkAb against the bounds of ourselves. This is going to require a hit info. We do not want to pass in the hit info that we received from the checkRay method, like the call stack over here, because what would happen then is if the ray contacts with the bounds of the node, then the hit info will be filled with information about the collision with the bounds of the node instead of with the stuff that's actually inside the node, which is not what we want. The axis line bounding boxes representing things that are like representing the collision world nodes don't actually exist in the world. They're just sort of helpful bits of data structure that are there to cut down on the amount of work that we have to do. And if you do a raycast against one of those said abs, then you shouldn't pass in a hit info. If I go into shapes, did I set it up earlier so that when you do a raycast against an ab or something, where's check ray over here? Okay, so I didn't write any code so that if hit info is undefined, you could just ignore it. You could do that. I feel like it's really weird that I didn't do that earlier. So you could only update the hit info if this is not equal to undefined or something like that. At this point, though, I don't want to make changes to the to the call ab raycast code, so I won't do that. So instead, I will just I'll just sort of cheat by passing in a new raycast hit info like that, and it's just gonna sort of be discarded as soon as we're done with it. We don't really care anything for example, the precise location in space where the raycast hit occurred, or the surface normal, or anything like that. We just want to know yes or no, was there a collision between the ray and the axis line bounding box. Next, since when you do a raycast into a group of objects, you generally don't want to know just yes or no, was there a collision? You generally want to know the location of the nearest collision. We're not just going to do a self.contents_i.check ray and then call it a day. We are going to instead let me fill out the argument lists to these function calls correctly. This is going to be check ray, which takes the ray as a parameter, and the actual hit info struct as a parameter. And that's going to be the case for both self.contents.checkRay and self.children.checkRay over here. And let's say I'm going to define var result is going to be false. And then instead of just returning true or returning false, we want to check everything in the Octree node. So we're going to, instead of returning, say result equals true. And that's going to be the same again in both these conditions of this branch, true and false. The only difference is what object exactly you are checking with the raycast. And then at the end, instead of simply saying return false, because this is the only return statement in this entire check ray method, we're just going to return result. Okay, that was a lot. Alright, I want to stop here because I've been talking for a long time and my throat is getting sore, but before I stop, let me go back up to call world, and we're going to finish some things. One is going to be accelerator's new call world Octree, And the bounds parameter that we're going to pass into the constructor is going to be self.bounds. The depth is going to be max depth, and that's going to be initializing our Octree acceleration structure. Add and remove, this is going to simply be a matter of self.accelerator.add object. Remove is going to be a simple matter of self.accelerator.remove object. Update, as I said before, this is very simply going to be removing the object and then re-adding it. Check object, we can simply, again, one line of code, return self.accelerator.check object, the object in question. Check ray is going to be a little bit more involved. We can say var hit info, because I did promise that I would create one of these and return it if a collision was found. Hit info is going to be new raycast hit information. And then if self.accelerator.check ray with the parameters of the input ray and the new hit info struct. If a collision is found, if a raycast hit is found, we're going to return hit info. Otherwise, we're going to return undefined. So if a raycast is detected against the world with a ray, then what is returned is going to be a raycast hit information struct containing all the relevant information. Otherwise, if no raycast hit is detected, we are going to return undefined. And that should be it for our collision world setup. Boy. This was a lot. I haven't actually tested any of this code today. For that matter, I didn't test any of the code yesterday, but it was last time rather. Last time was just a few simple variable definitions there, so I don't think it's as big of a deal. But I'm going to hold off on testing this until next time. If you're seeing this video being posted, then that means that everything I've written should work. If it doesn't work, I'm going to have to redo the entire thing over again.
Hey.
But next time, we're going to put our theories into practice, and we are going to do a collision world demo. And I'm going to be taking, where was it? This thing here, with its 1,000 collision objects, it's 50-odd frames per second, checking for the player's movement against all 1,000 of these collision objects, and some other hard-coded bits of awkwardness that can be cleaned up with the help of a collision world structure. And I will be inserting it into here, and we should see our frame rate going much, much higher with the help of a little bit of hierarchical organization in the form of an octree. So that's going to do it for me for today. Next time, well, I just said what we're going to do next time. After that, I'm probably going to take another bit of a hiatus from this 3D collisions thing, and then I'm going to come back to talk about matrices and some of the weirder shapes, such as oblique bounding boxes, oriented bounding boxes, whichever you prefer, capsules. I want to talk especially about some things such as collisions with terrain, because you can make some assumptions about terrain that might allow you to speed things up a little bit. More than you could perhaps with just one of these, like, general collision things, triangle meshes, whatever your terrain happens to be shaped like, as well as other miscellaneous things. I might actually start to get into, like, best practices when it comes to 3D collisions and stuff that I've been mostly avoiding so far. Anyway, if you want the code for this, look for the GitHub repository down in the video description. I'm really going to have to break this up into multiple commits because this is like 100 lines. I have a Patreon, so if you want to contribute towards these videos being made, look for the links to that in all the usual places. You could see some fun things like your name in the credits, hear a shout out of your username at the end of every video. About once a month, I post a bit of a preview of my future plans, and if you wanted to pledge, I would definitely appreciate it. Otherwise, I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Game, currently Bullet Hell. I hope you all found this useful, and I will see you all later. Hello all you crazy people out there, my name is Michael, I like wizards and dragons and making games, and welcome back to 3D Collisions in GameMaker. So this is the moment of truth. This is the day that we're going to figure out how well exactly all of the collision hierarchy and triangle collision code that we wrote over the past, I don't even know how many videos anymore, how well that's going to work in an actual game. So I'm going to take the 3D Collisions project that we've been working on, and I'm going to go, once again, tools, create local package. Publisher name can just be Drago. Display name can be I'm gonna call it collisions test. I guess the version can be like 1.1 or something because this is Act 2 as I've been calling it. The package ID and or file name can also be collisions test, and the actual project assets that I want to export are going to be just everything that was in the collisions stuff folder. All right. So we can save that. We can save that over whatever's already there. Open that in Explorer so that we can just drag it into GameMaker later. And let's actually open up the 3D collision test world. So this project is mostly the same as it was the last I left off. I've made a few changes. One is that now, instead of how many trees were there before, instead of down here, instead of 250 test tree objects in this 3D world, there's now 1,000, and that is much more computationally expensive than it was than it was last we left off. Also, I've added a little, when you click the left mouse button, there's a little raycast ball that goes and flies off into the distance. That is going to be used for testing raycasts soon enough. Right now it doesn't do anything. Okay. And in addition to that, I've made some changes to the way that things are drawn so that drawing is a little bit more efficient, and so that the debug timings that we're seeing actually are mostly to do with how well collisions perform. And I've also made some changes to the way that drawing things are done, so that drawing is a little bit more efficient. Drawing things in 3D space is a little bit more efficient. And any like lag that we see by way of the debug timers in the game will have more to do with actual collision code, more so than it'll have to do with actually drawing stuff, which is often what the bottleneck in 3D games is. So I'm going to take the existing collision stuff folder and delete it, and then I'm going to go and replace it with and if you drag and drop the like collisions test.yympс into the GameMaker IDE, it'll automatically prompt you to import it. So let's go and import the new collision stuff assets, and that's going to add both the updated scripts where those have changed, and also some things such as call world and SAT stuff that's been newly added. I'm going to call that a day. If I run the game now, it should be functionally identical to what it was before. All right down to performance, and the old collision shapes still work. All right, that's a good sign. There's no old things have broken. So a recap for how collisions were implemented in this project. It's pretty much all in the step event. It does it in 3 places. One, when the player moves, it checks for collision on the x-axis. It loops through all the trees in the game, checks for collisions on the x-axis. And then again, it does it on the y-axis, so it checks for the player's movement on the y-axis, and then it does it a 3rd time on the z-axis when you're jumping up and down. And as we can see, it works, it produces the correct result, but it's, one, it's kind of a pain in the neck to write this code to have to loop through every object in the world every single time you want to check a collision. And 2, it's a bit of a brute force approach that's not super efficient, and we can make it more efficient. So first, let's instantiate ourselves a little collision world. I'm going to do that right here at the top. I'm going to say collision world is going to equal a new call world. This takes 3 arguments. This is going to take a bounds min, which is going to be a vector 3. I'm going to mostly arbitrarily say new vector 3. Let's go with -2000, -2000, and why not? -2000 on the z, even though most of the things in this game are pretty much on the same plane. The bounds max, so the maximum bounds of the world that the collision volume is looking at, is going to be same thing, but in the positive direction. New vector 3, 2000, 2000, 2000, and the max depth, let's make that 3. So the max number of subdivisions that each cell in the collision world can occupy. Actually, you know what? Let's make that more like, let's go a little deeper. This is a big world. We can afford to make it 4 instead. So now that the collision world is initialized, we might as well start adding stuff to it. So the two types of 3D objects in this world, I'm going to actually, I think there's 3 types of 3D objects in this world. There's the floor, there are the trees, and then there's the player. So each of these types of shapes, oh, I guess there's the ball too, which I'll get to later. Each of these types of like game entities contains their own collision shape, which is either an ab or a plane or a sphere, or the ball is just a point that we're going to be raycasting from later. And to get these into the collision world, we are going to want to say collision world.add, and we are going to add ourselves an object, and this is going to be a new call object. The collision object, as you know, takes a few parameters, one being the shape, so the actual collision shape, spheres, boxes, whatever, and that is going to be... Why did I decide to just, like, doorbell? Alright, whatever. Why did I decide to, like, store the floor object in the array of trees? That seems a little bit silly. Anyway, the shape is going to be the floor.shape. The reference, so the object that we're going to refer back to with the thing in the game that this collision object is going to refer back to is going to just be the actual floor itself. And am I missing a parenthesis somewhere? I am. Very nice. And then when we instantiate each and every one of these trees, we can do basically the same thing. Collision world.add a new call object. The shape that we're going to add is going to be tree.shape, because remember, each of these tree objects have a collision shape as well, and the object that is going to refer back to, the entity that's going to refer back to, is the tree itself. Next, even though it's not going to be part of the collision world, although you could add it if you want to, because remember, objects don't collide with themselves, the player is going to need a collision object. I'm going to just, like, player.object. GameMaker allows you to tack on variables onto things after, like, outside the constructor, so I'm gonna take advantage of that power. Player.object is going to equal new call object. The shape is going to be player.shape, and the object reference, the entity reference, whatever you want to call it, is going to be the player. So this is all the setup we need. Let's go over to the step event, and now we can, instead of looping through all the trees and checking all the trees one by one for collision, we can say if obj underscore camera dot collision world dot check object. And remember, this code is running in the scope of the player here. So if we are detecting a collision between the collision world and the self.object, so our own collision object, then, and this is just going to take the place of the big ugly for loop over here, because it's going to do all the collision checking ourselves. Then we can just set dx equal to 0. And we don't need to break over there. Dx is the movement in the horizontal axis. On the x-axis, the terminology is a little bit stolen from calculus, but not too much. Hopefully nobody minds. And then we can do the same thing on the y-axis, so we can say when we check our potential movement on the y-axis, if the main game object's collision world.check object ourselves, if a collision is detected on the y-axis, then we won't move. And on the z-axis, it's going to be similar, but instead of saying like dz equals whatever equals 0, it's going to actually be z speed, because that is a persistent movement value, and that it accumulates over time because gravity. So now here's the moment of truth. If I run the game, we should have something that works just as it did before, and so far it does, but it performs much, much better. All right, cool. I got this working on the first try. It does not always happen when you're recording a video or a Let's Play or whatever. Alright, so if I hit, I believe it's the tab key, what is it, the Z key? We can see okay, tab was to unlock the mouse. If you hit the Z key, you can show the collision shapes. And you can see that each of the trees is where their colliders are. You can see where the player's collider is, and you can see where things are getting stuck and not being able to walk through the trees. And you can see now that the FPS reel has gone from, what was it before, like 40 to 50 range to 200 to 300 range. Hey. And that's definitely quite an improvement. If I do the little jump thing, I can, like, I'm not checking when I'm jumping to see if I'm actually on the floor, so I can just sort of fly here. movement on the z-axis is respected as well. So you can jump on top of trees, you can fall, and you can stop when you hit the ground. There's nothing special that prevents you from going below the floor, except for the fact that the floor's collider is there. Okay. All right. So much more efficient, and the code to implement it is actually quite a bit nicer, which I think is a win for everybody involved. All right, what next? Next, I'm going to deal with the ball raycast so that we can raycast into the world. But first, when I go into the 3D collision test world, and now let me look at the where are we? Objects. Let me look at the ball's code. So the ball is kind of a mini object. It has an update method. The ball has a step event, more or less. It's called update. The ball object itself is pretty simple. It has a position and a direction when it's instantiated, and then in the step event, all that happens is that it adds its direction, its velocity vector, essentially to its position, and that's it. It doesn't check for collision or anything. It has a collision shape, which is a point, and now that I think about it, I'm pretty sure I'm not actually using that. The demo world should work exactly the same with or without the ball's collision shape. So I'm just going to take that out for the sake of simplicity. So instead of doing this, let us go and do a little raycast. So I can say, let's create ourselves a ray. This is going to be the ray that represents where the ball is moving. The origin is just going to be the ball's position, so that is going to be self.position. The direction is going to be, well, now that I think about it, the ball itself shares quite a bit in common with a ray, doesn't it? It's just a point in space with a velocity, which is the same data structure as a direction. So I'm going to get rid of, actually, I won't get rid of that yet. I'll just comment it out. So do I have it open already? I do not. The world's check ray method, you may recall, instead of taking a hit info as an input parameter to the function call, to the method call, it's going to just create one on its own, and then it's going to return that if a hit was detected, and then it's going to return undefined if no hit was detected. So instead of having to say something like var hit info equals new raycast hit information or whatever, and then do that whole song and dance, we can just say var raycast result is going to equal obj obj demo. Is that even in this project? Oh, that's it's a variable that's referenced somewhere. If I was using one of the newer GameMaker betas with the Feather IntelliSense, it would probably give me a little bit of encouragement to remove that variable wherever it happens to be. Anyway, obj camera.collision world.check ray, and we're going to test this ray against the entire collision world, and we can say if raycast result is not equal to undefined, else. So if the raycast hits something, we can say if raycast result.distance, which is the distance between the ray's origin and the nearest hit location, if this is less than self.direction.magnitude, then self.position is going to be raycast results.point. And then we can just we can set our direction or velocity to 0. So self.direction is going to equal new vector 3 with a 0 on all of its components. Else, if the raycast in the direction of the ball's movement does hit something, but it is farther away than the distance that the ball should move in this current step, we can just we can continue on our merry way and worry about stopping when we hit something later. And then, of course, if the raycast result is equal to undefined, so if the raycast doesn't hit anything, we can also just continue on our merry way. Alright, so now when I run the game, we should see I'm going to go and throw the ball, and it's going to stick to the tree's collider. If I were to turn on colliders, you could see exactly where that lands. Alright, if I were to throw the ball somewhere like off into space, off in that general direction, it's just going to keep going to infinity. until I throw another one, and the ball's position is basically reset like that. If I were to, can I try and like aim right at the corner? It's a little bit difficult actually when the colliders are turned on, because I can't see where exactly I'm throwing. Yeah, you can see that if we throw the ball right at the corner of that collider, it's going to get stuck. If I throw it maybe a little bit higher, it's going to go off into infinity. It'll pass through the top of the tree because there is no collider up there. And it'll just keep going off into space to infinity and beyond. So that is raycasting against the world. There's one more thing, which is kind of the big thing that we spent this entire like last part of the 3D collision series doing, and that is collisions against triangle meshes. Let's see. I'm going to do a little bit more setup. First, I'm going to commit this. The raycast ball. The raycast ball detects raycast hits. That sounds really dumb. So I can load in a triangle mesh. So we have a couple of vertex buffers. We have like VB tree simple, VB tree cone, VB tree cone dark, whatever. I am going to do a little bit more. I'm just going to make a few changes to the test program so that I can actually get one of those in here. One of those is going to involve... Let me look at my notes. Alright, first when we actually draw the world. Okay, let me just copy and paste a little bit of code into this project, and this is going to be... I think the tree that I'll use for a test here is going to be tree plateau. In my test project for this, I used tree cone. But I think the plateau tree is a little bit more of an interesting shape and should provide a little bit more interesting collision behavior. So this is just, we're looping through the vertex data, and we are picking out each of the actual 3D position attributes of the vertex data, and we're just forming them into a triangle mesh, into an array of triangles. There's two buffer deletes here. That would cause an error, wouldn't it? If you don't mind me copying and pasting a second time, I'm going to just go down to the bottom of the where the trees are added to the collision world. I'm going to instantiate myself a new tree object. Again, the model which we can instantiate with can be a plateau style tree. Set its x position to 0, set its y position to 0, just to make things easy. Its shape can be a ColMesh instead of an AB. We are going to array push onto tree objects tree mesh, and the call object should just take two parameters, so the shape and the object. Okay, now this is going to spawn the tree at, I believe, the same location that the player spawns at, so let me just offset the player spawns. Okay, that's already happening. I thought the player spawned at the world origin as well, but it's just, the player spawns a little ways away from the world origin. So if I were to run the game now, you would see that the game would take a couple moments to start. Is the setup here timed? It is not timed. Anyway, this tree is, I want to say, about 500 vertices. This tree that's looking very prominently in the middle of the game world, it's about 500 vertices. It being there on its own doesn't really affect the frame rate. If I were to get close to it, it would, depending on where in the tree I was trying to detect collisions with. Denser parts of the meshes would obviously be a little bit more expensive. But the collision mesh being in the game world itself isn't really that expensive. This is why, slight tangent, but you might have heard that the precise collision checks with GameMaker sprite collision masks is very slow and expensive, and that's not really true for pretty much the same reason. GameMaker's built-in collision system uses something sort of like a quad tree. I think it's precisely a KD tree, which is partition space a little bit differently. And if two sprites, even if they have like precise collision mask set, if they're far away from each other in the game world, they will not go to the effort of doing expensive pixel perfect collision checks against each other, because the broad phase of the collision detection will discard collisions that have zero chance of overlapping. Anyway, as far as the raycast goes, you can see that if I were to throw the ball at, for example, the tree trunk, it would stick if I were to throw the ball at, and my aim is really bad. Come on. I'm lined up with the tree trunk, right? There we go. If I were to throw the ball at, like, the ball doesn't originate at exactly the same place as the mouse cursor does, which is a little confusing. If I were to throw the ball at the tree trunk, it would stick. If I were to throw the ball a little bit to the left or to the right, it would not. If I really had good aim, can I, like, there we go. I was trying to do that when I was practicing, like when I made this demo last night, and it was really hard to actually get the ball to hit the tree without being right in front of it because my aim is that bad. If I aim at the branches, the ball will stick, but if I aim, for example, slightly below or above the branches, the ball will keep going, and we have precise collisions happening with the raycast. Okay, so this system also works with 3D meshes, and all is well in the world. All right, how long have I been recording this? Hopefully it'll be a little bit shorter than the video in which I actually set up the collision world, because that one was a monster. Editing that one sucked. All right. So I'm going to commit this. Let's see, this is just going to be a 3D mesh collision demo. That's all the changes I'm going to make here. I think there is going to be one more video in, like, Act 2, like an epilogue to this part of the 3D collision series. And that is going to be, I mentioned a few times, assigning collision masks to objects so that you can filter collisions and have only certain objects collide with certain other objects. And I decided against doing that, like, now as part of this video because I thought it would be a bit much. And it wasn't really related to the main point, but I do want to do it before I take, like, another 3-month break from 3D collisions, so there's probably going to be that. And then after that, I will most likely take another break from 3D collisions, and I think we are going to start dealing with matrices and rotations and other transformations in space, as well as rotated objects, rotated bounding boxes, things like that. I do want to talk about capsules. Capsules are generally pretty important in the world of 3D collisions, and I have not really talked about them yet, because they're a better approximation of things like the player character and NPCs than just a sphere or a rectangular prism would be. I also want to talk about other collision hierarchies that you might want to use. The way that collision objects are distributed, or even their specific use case in your collision world, can mean that certain types of hierarchies are better than others. For different situations. For example, one of the weaknesses of Octrees is that if you have a very dense collision world, you tend to see diminishing returns over just having a list of objects, because multiple collision objects can end up in the same, like, cell of the Octree, the same node of the Octree, which is not ideal. 3D terrain, because I just have a weird obsession with 3D terrain, is kind of its own thing. You can occasionally make some assumptions about 3D terrain that would allow you to add some terrain-specific optimizations. I'm trying to think if there's anything else I want to talk about. Best practices, I guess, or at least, like, my recommended practices when it comes to doing 3D collision worlds or something that could be fun. There's also the matter of, and this is a very dangerous subject, but implementing micro-optimizations, as some might call them, in your GML to make it faster without, like, changing the math, but just doing more efficient GML operations. That could be fun. I'm tempted to make a video on that, but I also don't want to, like, accidentally incur a new wave of people who are trying to micro-optimize their code instead of actually improving their algorithms, but that sounds like a problem for future me, which also happens to be my favorite kind of problem. So, my name is Michael. I like wizards and dragons and making games. This has been 3D Collisions in GameMaker. If you want the code for this, look for the GitHub repository down in the video description. Look for the, I guess, 0.2 on this test world, and I want to say the main 3D Collisions project is like 0.19 right now. Working out of multiple GitHub repositories in a single video is confusing. I have a Patreon, so if you want to contribute towards these videos being made, look for the links to that in all the usual places. You can see some fun things like your name in the credits. About once a month I make a post regarding future plans for future video subjects. And if you wanted to pledge, I would definitely appreciate it. Otherwise, I try to post about 2 game dev videos a week, one tutorial like this, and one let's make a game. Currently bullet hell. I hope you all found this useful and interesting and fun, and you can all now go and create your own 3D platformers in GameMaker, and I will see you all later. DJ Kibbles, Brenton, Bokeh Dev, and Arger the Knot for supporting these videos. If you would like to join these wonderful people, head on over to the Patreon page down in the video description to join the fun.